Hey folks, how's it going? This is Mr. Moray coming to you with a recap of the Hitting the Slopes midterm review. I thought I'd make this video for a few reasons. One, to help make sure you have an interactive set of answers so that you're not just looking at the answer keys saying, hey, where does this stuff come from? And also so that you got a sense of, actually what the answers are. Of course, if there's any errors or anything in there, that's something we can identify. I did put this packet together fairly quickly. One, to give you enough time to do it and have really all of January to do it and to work on it if that's something you want to do, but also to give you like a substantive review. The one thing we're not going to see come up on this is square root functions and cube root functions, the graphs of them. And that's why I assigned the in-class project that we're going to do, or rather the project that we're going to do, maybe in class, but probably not. And also, one thing that's not going to come up here is parabolas, especially. As you can see, there is work on circles. There may be work on circles, but not parabolas, because that was stuff we just freshly did in class. So that's something that we should be pretty good on at this point, and if not, you want to seek out the extra help. Okay, so I'll just quickly take a moment and walk through what's going to be on this packet. So we have going all the way back to August, September, analyzing quadratics, solving quadratics, and by that I mean equations. We had complex numbers, we had factoring polynomials, and that kind of went into quadratics as well, but I was thinking specifically higher order than quadratics. Special factorizations, which means difference of squares and cubes, and quasi-quadratics, adding, subtracting, and multiplying polynomials, dividing polynomials and analyzing the remainders, solving polynomial equations, graphing polynomials, regression with polynomials, right? This was getting into the second term. Composition of functions, inverse, rational exponents, simplifying radicals, radical arithmetic, equations with radical exponents and radicals. So that kind of got towards the December break. And then when we came back in January, we started with conic sections, specifically circles and parabolas. And on this packet, we'll cover circles. And then there will be a contextual question as well. I put the varies here in terms of the heat level because I did take this context from another source. And that source, it was really, as they created it, it was varying levels of heat. It wasn't really built in the way that I usually do it. All right. So as again, we're hitting the slopes. We have our straightforward contextual ideas. Like what are the concepts? Okay. Then we have our medium level problem, our hard problem, and our super hard problem. Okay. So I'm going to go ahead and I'm going to jump in to the first section, and that is analyzing quadratics. Okay. And so here we go. So to begin, the graph of a quadratic function, okay, what is it called? Well, we know what that's called, hopefully from 9th grade. This is called a parabola, okay? And remember, at the beginning of the year or coming into the year, we knew of an up and down parabola. And then as we went, we talked about conic sections. We learned about the left and the right. But function, I only want the functions. These are the only parabolas that are actually representative of functions because they pass the vertical line test. Okay, for any quadratic, we can have 0 x-intercepts, 1 x-intercept, or 2 x-intercepts. Okay, because that has to do with the number of times that the underlying equation or formula is equal to 0, right? And we call those the zeros. Okay, and so the number of x-intercepts when we are in, and remember this is called standard form, okay, is determined by what we call the discriminant. The discriminant essentially discriminates between when there are 2, 1, or 0 real zeros, okay? And remember, we're always graphing. When I make a graph, these are always the real numbers. So for all intents and purposes here, with regard to the discriminant, I only care about the real zeros, okay? And remember, the discriminant is the b squared minus 4 AC, right? So remember the quadratic formula, this is the stuff under the root. All right, now there are three forms of a quadratic. We have standard form down here, and then we have vertex form. Okay, we have factored form. Okay, and that might have been a typo on my end. So it should look something like this. A times x minus p times x minus q. Shouldn't be there, so I'll rewrite it. It looks like this. X minus p, x minus q. Okay, and p and q are essentially the numbers that represent the x-intercepts. Okay, so for example, x minus 3, x minus 1. Remember, this is also called factored form because it's what it looks like when you factor the quadratic, right? So here, x minus 3, x plus 1, x-intercepts are easily seen, and they're 3, 0, and negative 1, 0. Okay, and then standard form, which is how we often see it. Okay, we have the coefficients. We notice how we have the powers of x, 2, 1, 0, or no x there in descending order. Okay, and that's how we learned a polynomial in standard form in general is supposed to look. Okay, so what we need to do is we need to determine the discriminant of each function, or rather whether it's positive, negative, or 0. This was a really good test question that we talked about when we talked about the discriminant. Okay, so remember the discriminant tells us the x-intercepts. How many are there? And the formula and the a, b, and c when we have a graph don't really matter, right? So here we can see there's one x-intercept here. There are two x-intercepts here. And again, what the x-intercepts are don't really matter. They turned out to be clean, but that doesn't really matter. Okay, I just want to know how many there are, and I need to think about how does that relate to the discriminant. So here we know the discriminant is equal to 0. Okay, and that's because when the discriminant is 0, when I do the quadratic formula, right, there's only one square root of 0. So there's only going to be one underlying solution. Here, the discriminant is less than 0, right? In other words, it's negative, and I know that because if the discriminant is negative, when I take the square root, I don't get a real number. Therefore, there are no real solutions. Okay, and finally here, the discriminant is positive because when you take the square root of the discriminant when you're doing the quadratic formula, you get two real numbers, right? Meaning there will be two real zeros. Because remember, we only care about the real zeros when we are graphing. Okay, now I'm going to come down and look at these ones. So write the equation of a parabola in any form that meets the following criteria. 1, positive discriminant. 2, and maybe I'll make that a checkbox. Okay, 1, positive discriminant. 2, the end behavior is as follows. As x goes to infinity, f of x goes to infinity, and as f of x goes to x goes to negative infinity, f of x goes to infinity. The axis of symmetry is at x equals 3, and one of the x-intercepts is 6, 0. So let's take a look and think about what does this mean here. So we need to write in any form. So like for me, the first thing I notice here is I notice that the axis of symmetry is given and one of the intercepts is given. So if I'm going to write this in vertex, intercept, / factored, or standard form, which one do you think makes the most sense? I'm thinking for me, what makes the most sense is we're going to put it in factored form. Now, the other thing I know here is I happen to know that because there's a positive discriminant, that means that there are going to be two x-intercepts. So what I'm going to do is I'm going to set up my factored form. Now, it doesn't really matter what we set as our a value here. It doesn't, basically, right? We know that the end behavior is infinity on one end and infinity on the other end. And that basically tells us that the a value, in other words, the number right here, it needs to be positive, okay? And so if we can make that a value positive, then that will force the parabola to point upwards, right? Because when a is positive, so here's an example. A is more than 0, a is more than 0, and here a is less than 0 because that makes it point downwards, okay? So now here I go. I need to fill in x minus 6. There's my first piece because I know that when x is plugged in or 6 is plugged in, it makes this 0, so the output will be 0. So I've checked this off. And now I know that the axis of symmetry is at x is equal to 3. So if I were to zoom in on this parabola, zoop, zoop, here is 6, 0 in action. And here, boop, 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 this is 3, okay? So what that means is in order to meet the symmetry, well, I know the other intercept has to have the same y. So to have the same y, the x of this x-intercept has to be the same distance away from the axis of symmetry as the other x-intercept. That's what we mean when we say symmetry. And that means that this has to be 0, 0. Okay, and again, 0 is 3 away from 3. 6 is 3 away from 3. Therefore, they must have the same y value. So I fill that in. Okay? So now that's going to ensure an axis of symmetry at 3. The discriminant is now positive, and I know that because now I've locked in 2 x-intercepts. There's 2 x-intercepts, therefore the discriminant's positive. And finally, you could leave it as this. You just want to make sure there's now a positive number. If I leave just nothing, that means it's positive 1. So this is actually okay. The other way you could write this is as x times x minus 6, or you could write it as x squared minus 6x. Any 3 of these would be acceptable for this problem. Okay? All right. Now I'm going to come down to the next part here, and in this next part, I'm looking to write the equation of a parabola in any form that meets these criteria. So now I need a negative discriminant, meaning how many x-intercepts? None. Okay, now I have the end behavior, infinity, negative infinity, and negative infinity, maximum value, and a point it passes through. So now I'm given a maximum value, and that tells me that I'm going to use vertex form because the maximum value implies that the y of the vertex is negative 4. I don't know the x, but I do know the y. Okay. Now, what the x is doesn't necessarily matter, but we do want to make sure that the end behavior is down in both directions, and that means that the a is going to have to be a negative, the leading coefficient. And the reason that it has to be so is because we want the parabola to point downwards, okay? And the only way that's going to happen, right, is if a is less than 0. And if we have a negative discriminant, as long as I start below the x-axis, if a is 0 and it points down, I'm never going to actually hit, okay, the x-axis, right? Because I'm below, I'm pointing down, there's no way to get up to it. So therefore, I'm not going to have x-intercepts. And therefore, the discriminant is going to be negative. All right, so now I need to see what I'm going to do right now. And I actually do have a lot of freedom. I noticed that 120 has to be one of them. I think you actually, folks, have a lot of options here. So let's set up vertex form. F of x equals a. We don't know a yet, but we could figure it out. Now the a is gonna be how we get it to go through this point. I'm gonna do x minus 4. So that means the maximum value is 4. Let's see. What do I want to do? Well, we know that if a was negative 1, we might have remembered from last year that's going to go down by 1, down by 3, down by 5, down by 7, right? And so maybe what I'll do, it needs to go through 120. maybe what I'll do is, I don't know, maybe I'll make it a 5 and see what happens. That's just my choice. You can label it, you can really, in this problem, you can make h whatever you want, right? I never said what what h had to be. I only said that the maximum had to be 4. And remember, maximum also is going to imply a negative a, because if it's a maximum, a is negative, it hits a top. If it's a is positive, it's a minimum, you get a bottom, okay? So right now, here's what we've got. We have this setup right here. Now, if y is equal to 20, what that means, or rather negative 20, what that means is that x has to be equal to 1. Okay? So let's see what happens. So if x is equal to 1, 1 minus 5 is equal to negative 4. Negative 4 squared equals positive 16. Now I add 4, I add 4. Negative 16 equals 16a. Okay, and then I've got a is equal to negative 1. So if it seemed like I was pausing earlier at this point, that's because in my head I was trying to concoct a better number, and choosing 5 makes this come out nicer. Again, if you had chosen, I would have not chosen probably 1. You can't choose 1. If you had chosen 2, if you had chosen 10, it wouldn't have really mattered. It would have just made your a a little bit more of a difficult calculation. It would have made it turn out as a fraction, but it doesn't really matter. Okay, so here's what I know. Now I plug in negative 1. And now check it out. I've got a maximum at 4. It's a maximum because a is negative. I have a negative discriminant because I'm below the x-axis and I'm pointing down. So I have no x-intercepts, so I have a negative discriminant. Okay, I could also FOIL this out, right? In theory, this is x squared minus 10x plus 25. So it's negative x squared plus 10x minus 25. So when you add minus the 4, it would be minus 29, okay? But then if I plug this in, it would be 100, and then these would cancel, so it would be 100 basically minus 120, so you'd have a negative discriminant. You could plug it in and find it out, but remember, if you know it's never going to hit the x-axis, it's not going to ever have a positive discriminant, okay? And finally, the a being negative 1 ensures that it passes through the point 1, negative 20, okay? And so with the single black diamond, we were really shoehorned into one possible way to do it. Though, in theory, we could have made the a value whatever we wanted here. Here, we had some freedom with regard to what we chose as the x of the vertex, but then once we chose the x of the vertex, that in turn determined the a value. Okay, so go ahead, take a moment and make sure you understood what we did here in this first part. And then in a moment, I'm going to go ahead and move on to the next part. Alrighty, wow. So I'm going to go ahead and move on. And here we go. Solving quadratics. Oh, I love solving quadratics. Again, a recap from last year, at least for now, for this year. And so solving quadratics, there's 4 ways to solve quadratics, okay? There's square roots, okay? There is factoring, okay? There's completing, you could complete the square, otherwise known as CTS. And then there is the quadratic formula. Okay, we need a way to solve it. We have the nursery rhyme, right, etc. B squared minus 4ac all over 2a. Okay, And remember, for 2 and 4, you have to have the equation equal to 0 for them to work. Now, mostly this applies to a quadratic that's in the form ax squared plus bx plus c. Generally, it has to be in that form. If it's in like a vertex form, the square is already completed. You'd have to do a combination of maybe like square roots, etc. But generally, it's when we're in this form right here. And so, again, you have to think about, and it was kind of like I was a little bit shook a little bit when we were doing the most recent unit, and people didn't know how to execute on these, because what we did in the circles and systems, etc., goes back to what we did right here. Okay, so here we go. So I'm in this one first. Now notice, you see that there's no b value. There's only an a and a c. So if I was going to say what methods would I use, I could use the quadratic formula. Provided that's equal to 0, the quadratic formula always works. However, I'm going to have to square 242. Or no, rather, I'm going to have to multiply 242 by 2. It's going to be 484. I'm going to have to know how to square root that. And it might not be obvious, right? Now, we do know that, and then, I'm going to have to multiply that by 4. So I'd have to do 2, 4 times 2 times 242. I have to square root it. I have to do all this kind of nonsense. And I mean, that's not wrong. It'll work. But is that the best use of time? I would argue no. Completing the square is a bad idea because there's no b. So how do I complete the square, right? Completing the square usually requires you to have a b value. And in any case, a is more than 1. Factoring would work if it was a difference of squares, though we know that 2 is not a square. And if I take the square root of 242, that's not a square either. So the easiest method here is actually going to be solving by square roots. So the first thing we're going to do, and notice that 242 is divisible by 2, we're going to isolate the x squared. I'm going to divide by 2. And then I'm going to take the square root of both sides. And so either x is equal to 11 or negative 11. And if we weren't sure, now notice our calculator only gives us the answer of 11, because the square root of 121 by definition is 11. But we're not in this case taking the square root of 21 and saying that's it. I'm saying what x, when I square it, gives me 121, and the answer to that is 11 or negative 11. Because think about it. If I square 11, I get 121. But if I square negative 11, I also get 121. So both those answers work, so both those numbers have to be solutions. Okay? How about this one? Well, this one's not equal to 0, so let's start by making it 0. X squared minus x minus 42 equals 0. Now I'm going to factor this. Well, good news. I'm going to make my box. Okay. Here's x squared. Here's negative 42. These have to add up to negative 1. And one of them needs to be negative. Okay, so for example, this is x and this is x to get x squared. So one of these numbers is negative and one of these is positive. And I know that because they have to multiply to a negative, and a negative times a positive is a negative. The negative needs to be greater because when they add, I have to get a negative. So what I'm thinking is negative 7 and positive 6. Okay, because if we plug these in, this becomes a 7x and a 6x. So this adds up to negative 1x and multiplies to negative 42. So what I'm looking at is x minus 7, x plus 6 equals 0. And now I get x is 7, and I get x is 6. Okay? Lastly, up here, what I would do is, this is a tough one. So what I'm thinking I want to do here is I'm going to move the 3x over. So 2x squared minus 3x minus 2 equals 0. Now I'm going to do some factoring. All right, how do I get 2x squared? Well, this needs to be 2x and this needs to be x. That's the only way to multiply these and get 2x squared. Now, to get negative 2, one of them needs to be negative 2 and one of them needs to be 1, right? It's the only way to multiply and get negative 2. Now, I need to multiply, and I need to, ultimately add to 3. So if I put negative 2 here, then this will be negative 4x. And if I put 1 here, it's negative 4x plus x, so it's negative 3x. And that all multiplies. Beautiful. And so now, if this is 0, x is equal to negative 1/2. And if this is 0, x is equal to 2. Okay? Because remember, when two numbers multiply to get 0, one of them has to be 0. All right. Now the diamonds. So again, we're in a situation where we're needing to solve quadratics. Okay, I want it equal to 0. So you want to generally keep your a value positive here. All right. So what I'm going to do is I'm going to move everything over. So I'm going to subtract the negatives, subtract the 17x and add the 10. So I have 3x squared minus 17x plus 10 equals 0. Okay, I would check for a GCF, but I know that 17 is a prime number, which means that nothing else other than 17 and 1 is going to go in. So I'm going to say, let's try to factor. Okay, when I see like a number like 3 next to the x squared, I know that there's only one way to get that, and it's going to be this. Okay, and so now what I'm going to do is, let's see if I can finagle a 10. So the 10 is probably going to be a 5 and a 2. I know that this is a positive, so either I have negative, negative, or positive, positive, but they're adding to a negative, right? So you have to use some reasoning here. If you see that C is positive, and the last two numbers are what multiplies to C, well, you only get a positive when it's a positive times a positive, or negative times a negative, right? Whereas here, I saw a negative, so I knew only one of them was positive, and same here. Here, I know they're both negative because they add to a negative, right? When I do all the addition, and the only way to have two numbers add to a negative and multiply to a positive is both of them have to be negative, okay? So let's see what I can do. Well, I notice that 3 times negative 5 is negative 15, and negative 2 times x is negative 2x. So I have 3x squared minus 15x minus 2x plus 10. Perfect. So here I'm going to get x is 2/3, and here I'm going to get x is 5. Because if this was 0, first I'd add the 2, then I'd divide by 3. Okay, how about this one? This one I'm going to do a similar thing. So I'm going to add the 2x squared. I'm going to subtract the 5x, right? Get rid of everything on that side. So heck, let's go for it. Let's factor. So again, only way to make 2x squared. Now on the other hand of things, I'm going to need to clear out that left-hand side. And so in order to do this left-hand side, I am going to have to go ahead and I'm going to have to ensure that, well, everything's good, but now I got to ensure I got to get 7. Sorry, I'm kind of spacing here. So get 7, what I need to do is Well, I know it's going to have to be, can I get a 7 and a 1? I don't know. Oh, well, here's what I'll do. Ready? So, I'm going to do this. I'm going to put the negative 7 here so that this is a negative 7x. And then I'm going to put the 1 here. Nice. So this is 2x squared plus 2x minus 7x. So that's negative 5x. Uh-oh. But can I get the negative 7? Oh. I don't think so. So this one we might have to do the quadratic formula. All right. It's always worth a try. You always want to go low energy if you can. So x is equal to negative b, so it's 5, plus or minus the square roots of 25, which is negative 5 squared, minus 4 times 2 times 7, all over 10. Okay, so if I look at this, let's go ahead and move this. If I look at this, let's do some math. So I have 25 minus 4 times 2 times 7. Okay. X equals 5 plus or minus the square root of negative 31 over 10, which is equal to 5 plus or minus I times the square root of 31, or square root of 31i over 10. Remember, last year we would have left this as no solutions. This year you do need to find the solutions. Okay, so that would be where we'd use the quadratic formula. Now, if this was true, right, which we know, look, factoring is never going to work. Okay, because factoring only would get you real zeros, and this actually showed there were no such zeros. So look, I try to factor first. It's always good to shoot for a factorization if you can, because it's easier, but again, not always practical. Over here, notice that I have a GCF. So what I would do here is I would start by dividing everything out by 2. Remember, you can do this when solving, but not when factoring. Okay, so I divide everything out. I get x squared plus 6x equals 10. Now I'm going to complete the square. So I'm going to take 6 and divide by 2, and that's 3. Then I'm going to do 3 squared equals 9 and add that on both sides. So x squared plus 6x plus 9 equals 19. I factor. Okay. I'm going to move this down here. Now I square root both sides, so I get x plus 3. Maybe I'll take the parenthesis off. X plus 3 equals plus or minus the square root of 19. And so x equals negative 3 plus or minus root 19. Those are the solutions. Okay? All right, so make sure you understand how to do this up to this point. If not, I do really encourage you to go back and take a look. Okay, so now over here, 4x squared equals 17x minus 2. Again, I want to get it equal to 0, so I would do 4x squared. I'd subtract the 17x. I'd add the 2. You could try to factor it. I can't think of a good way to do that right now because you have to get negative 2 and negative 1. And off the top of my head, I can't get it to work. Here's one thing we might want to try to do. Here would be a good strategy. What if we try to plug it in? 4x squared minus 17x plus 2. See what the graph looks like. See if we can see it. Ooh, okay. Interesting. See if we can get a little trace set up here. Huh. All right, that's a good sign. But to me, it's a sign that we're not going to get a whole number. Right? They look like they're just, if I just take the trace off, looks like it's just a little bit beyond the mark. So it's not going to work. Another thing I could do is I could investigate. I could hit 0. And I could try an intersect. Trace 5 for intersect. Hit 1. Hit the second. And you can see it's going to be not a whole number. Okay, so that means factoring is not going to work here if it's like it looks like it's an irrational number. So we're going to have to quadratic formula. So the good news is that shows us that we should expect to find 2 numbers. Okay, so 17 squared minus 4ac all over 2a, which in this case is 8. Let's go ahead and do that out. So just to verify, 17 squared, it should be 289. Good. So 17, you don't want to guess at these things, especially if you have calculator access. And then 16, that's 32. Okay. So let's get square root. Okay, it's not going to be a whole number. So it will be 289, 17 plus or minus 2, 5, 7 over 8. Just a hair more than 16. What a pain. Because 256 squared is 16. Let's check it for divisibility, see if we can clean that up any. So is divisible by 4? No. Is divisible by, let's see, 9? No. Is divisible by 16? Obviously not. 25? No. 36? No, because it would have to be an even number, and this is not. 49, we could check 49. 7. 49 and 257, no. 81, just couldn't hurt. I don't think so, because I think it'd be 243 is the closest one. 257, does 81 go into it? No. So at this point, I don't think we can clean it up at all. So I think we're going to just have to leave it like this. And that's basically what we're going to have. So notice how this is 16.03. So if we do 17 minus the square root of 257, take the answer and we divide by 8, we get negative 1.2109, blah, blah, blah. And now if we do the intersection, it should agree with that. Intersect 5, 1, 2, 3. Yep. 121099756. 121099756. So we do have agreement on the graph. That's a good sign. Okay. So we might just have to leave things like this. Okay. Over here to the next one, what I'm going to do is, I don't like this. I don't like a number that's not 1. So I'm going to multiply everything by 2, which I'm allowed to do because it's a it's an equation rather. Now I'm going to get it equal to 0. So x squared minus 14x minus 10 equals 0. I can see there's no way to multiply to 10 and add to negative 14. But I can see that because this is a negative, instead of subtracting 4ac, I'm going to end up adding 4ac, right? Because it's minus 4ac, but when c is negative, the minus turns into a plus. So I'm going to quickly erase this. Actually, maybe I can get that back. All right. I'm going to move this over because I do want to save this if I have an answer key. And let's see what we got. So let's make a little barrier here. And let's start doing this. So x equals negative b, so it's positive 14 of, so 14 times, so I would definitely give you a calculator if I was asking you to square things like this. 196 plus, because the minus turns into a plus, 4 times a times c all over 2a. So it ends up being 196 plus 40. And 236 definitely does not have a perfect square. And we can actually verify that. No. Okay, so it's, let me just separate this. X equals 14 plus or minus root 236 over 2. And let's see if 236 is divisible by any perfect squares. So it's one where you'd feel like 16 would go into it, but it doesn't. But 4 does. Because if the last two digits are divisible by 4, the whole number is. And 59 is a prime number, I believe. So we have 14 plus or minus, so 236, we have a 4 and a 59, so it becomes 2, which is square root of 4, square root 59 over 2. Now we got to do one more cleanup. This cleans up as 7 plus or minus just the square root of 59 over 1, which we can leave as this. Okay, so definitely some difficult problems. Please make sure you go back and understood where these came from. And then in a second, I am going to move on to the next set of problems. Alrighty, moving on to complex numbers. So a complex number is any number in the form a plus bi, and the conjugate of a complex number is another complex number in the form a minus bi, okay? And if we multiply these, the effect is that it dismisses or gets rid of the imaginary part, so you get a squared plus b squared, right? Because this would ordinarily be, it's a difference of squares. So it'd be a squared minus b squared, or plus rather, b squared times, nope, it would be minus. Let me go back. So it'd be a squared minus, because you do minus b squared ordinarily. But because the I squared is also there, and I squared is negative 1, it turns it into a positive b squared. Okay? So remember, the idea of the complex conjugate is that the complex conjugate, it always cancels out a negative, it cancels out an I, and it makes everything not imaginary anymore. Okay? So here what we're going to do is we're going to go ahead and just do some arithmetic. So when we're doing arithmetic with complex numbers, first we just, in case of subtraction, we subtract the like terms. So we do 2 minus 2, those cancel. So we have negative, so what remains is negative 3i minus negative 5i. Okay, and those cancel, and you get 8i. Okay, here, negative 6 plus 7 is 1. 13i plus negative 2i is 13i minus 2i, which is 11i. Okay, so it's 1 minus 11i. Let's make that circling a little bit clearer. Lastly, we have 62 minus negative 12, negative 45 minus positive 13. So down by 13. And that's how we do those. Okay, here, this is where we struggled and where I warned you from the jump that we would. Okay, so I want to box these. So we have 3, 5i, 2, and 7i. So I have 3 times 2 is 6. 2 times 5i is 10i. 3 times 7i is 21i. 5i times 7i is 35i squared, but i squared is negative 1, so it's negative 35. So I have 6 minus 35, that would be negative 29. Then I have 10i plus 21i, so that'd be 31i. So remember, the biggest mistake people make is they forget to make the I squared into a negative 1. I've said off the jump that happens every single year. People don't do that. Please do not let that be you. Please remember to make I squared negative 1. If I see I squareds in your answer, that's like we can't still have that happening. Okay, so we need to get past that. All right, on to the next one. This is just, all this is here is 7 minus 9i and 7 minus 9i. Okay, so we're going to do a similar thing. Set up our box, Okay, and let's hook it up. So 7 times 7, 49. 7 times 9i, negative 63i. Again, a negative 63i, because it's 9 times 7. 9 times 9 is going to be 81i squared, which means it's negative 81. So I've got 49 minus 81. Then I've got 63, negative 63 plus negative 63. That's negative 1, 2, 6, I. Okay, that's all we can do. All right, lastly, notice that these are conjugates of each other. So I did this so that we could think about, again, what's going to happen when we do conjugates like this. Okay, so let's take a look. 12 minus 4i. 12 minus plus 4i. So 144 minus 48i plus 48i. Okay, so what's going to happen here? Canceling. Now, negative 16i squared. The I squared cancels, making this a positive 16 because I squared is negative 1. So it's 144 plus 16, which is 160. So again, notice what happens is this cancels out all i's and brings us back into the real universe where we only have whole numbers. And notice that it's a squared, 12, plus b squared, which is 16 rather, for a total of 160. All right, lastly, I'm clearing up some denominators with I in them. So remember, for here, what you're doing is you're multiplying by the conjugate, and if it's a monomial, rather one term, it's just whatever is down there. So the 2i and the 2i, that's going to become 4i squared. In other words, negative 4. Up top, you're going to get 4i. This is going to be 10i squared, or negative 10. And now we do need to clean this up because it says simplify. So we need to divide everything by 2. So that's 2i minus 5 over negative 2. And if we're being technical, what I'd like to see is a negative brought out front. And you could do a negative 5 plus 2I over 2. I don't know if I'm going to be that picky about the order, but if this was to come up in a multiple choice, you might have to identify that this would be the correct order. So maybe in a multiple choice, I'd put the real number first, because if we're going to stick to correct complex number form, this is correct complex number form. All right, in the second part, here I go. 12 minus 5i. I'm going to hook up the conjugate. So here, what I'm going to get on the bottom is this will be 144. If I FOIL this out, this will cancel because we'll have negative 60i plus 60i, then negative 25i squared. So what it really is it's 144 plus 25. Okay, give me 169. On the top, what I'm going to get is I'm going to get 36i minus 15i squared, which becomes a positive 15. And these all do have a common factor of 3, so I'm going to do two things. I'm going to put the real number first and divide out everything by 3. So this becomes 5. This becomes 12i. This becomes, let's see, is 169 divisible by 3? Did I make a mistake? Ooh, it's not. All right, so actually it turns out I cannot clean this up. So it actually turns out I'm good. So maybe what I'll do is I'll just rearrange. All right. Okay, and lastly, I'm going to go ahead and do this one. 7 minus 3i, 7 minus 3i. So here you get 49 plus 9. And 49 plus 9 58. Up here I'm going to get 14 minus 6i minus 6i minus 21i, and then after the minus 21i, I'm gonna get negative 9. So I have 5 minus 8i. Wonderful. Okay, and no way to clean that up. Okay, so again, hopefully this section made sense to you. I do encourage you to go back and see if you have any questions and make sure you understand all these problems. And then in a moment, we are going to move on to the next section. Alrighty, we're going to go ahead and move on to the next one. Sorry if there's any kind of weird jump here. I did have to kind of reset things in between this part and the next part, but we're going to go ahead and move on to factoring polynomials. Okay, so this kind of goes back a little bit earlier, and I'm pretty sure that I do have a video on this, at least when I was going over one of the quizzes. So I'm going to try to link to that now. If I do have a video on this, the link's going to appear right up top at this point, and I encourage you to click on that and take a look at that. Okay, now factoring, and it's really good that we go over this because I saw some gaps appearing for some students when we got to solving systems with circles and semicircles, etc. When I asked them to factor, and I got kind of like some blank looks. Okay, so quick ways to factor. Okay, so you want to start by trying to remove any greatest common factors. That has to happen first. You have to try to get any GCFs out of there, whether that be a number, whether that be a power of x, or whatever other variable. Okay, when there are 4 terms, okay, you really want to start by, you want to think about factoring by grouping, okay? And again, that's something that I'm very, almost like 99.9% sure I've talked about in a previous video. When you factor by grouping, you may have to rearrange the terms first, because factoring by grouping has a really strong dependence on GCFs, and so you might have to rearrange to get that GCF to come out, okay? A few other reminders. If the leading coefficient is negative, you do want to start by factoring out a -1. And the reason you want to do that is because you want the leading coefficient to be positive if possible. And that will just make everything easier for you. So I strongly recommend you do this. If you can get it to factor without doing that, I'm not going to mark it down. But at the same time, I think it makes it easier for you to try to do that. Okay? And then finally, after each step, you need to go back and look at every single, so each factor, and see if it can be factored further. Okay, so for example, let's say you've gotten to the point where these are your two factors. So we have 2x plus 2 and 3x minus 1. You then go through this one here and you factor out a GCF, okay? You take the 2 out of there. Similarly, let's say you do a factoring and you have this, you get to this part, x squared minus 9, x minus 1. You need to come down here and do, this is x minus 3, x plus 3, x minus 1. So you've got to break things down as far as you can. In general, once you get to any factor that has the biggest power of x1, such as these, and there's no GCF, in general, you're going to be done, okay? So that's one thing to think about as well. So let's move on and think about these factoring problems, okay? So to start, let's take a look here. I've got 3x squared plus 12x minus 36. The first thing I'm going to notice is that there is a GCF of 3, so I'm going to take out the GCF of 3. Okay, 3 times x squared is 3x squared, 3 times 4x is 12x, 3 times negative 12 is negative 36. And now I'm going to factor the inside. This is something we need to know how to do from last year, okay? So I need two numbers to multiply to negative 12 and add to positive 4. One of them needs to be negative because I need to multiply and get a negative. So I'm going to choose x plus 6 and x minus 2. They add to 4. They multiply to negative 12. Remember, one of the biggest mistakes people are making is they go x equals negative 6, x equals 2. No, you're not doing this. There's no equation. If there's no equal sign, then I don't want to know what x equals. X doesn't equal anything. There's no equal sign. You leave it like this. Okay? So here again, we've got 4 terms. We want to go ahead and think about factoring by grouping. Okay? So again, what I'm looking for is I'm looking for a GCF that I can take out of 2 of the terms. And when I take out the GCF on the 2 sets of terms, so in this case, it's going to work out like this. Okay, in this case, it's going to work out such that this is the first set, this is the second set. So these are each going to have a respective GCF. When I remove the GCF, the things inside of the parentheses that remain should be the same. Okay, so let's look at this. The GCF here is x squared. So that becomes an x plus 3. Here, what I'm going to do is I'm going to take out a 2, and what I'm going to get is an x plus 3. Okay, because these both have a 2 in common, and that's it. These both have an x squared. Okay, and so notice when I do this, the x squared plus 2 comes out, and what I'm left with is an x plus 3. Okay, so now we come back and look. Can I factor x squared plus 2? No, I cannot. Okay, and the reason I know I cannot is because if I was to try to solve this, I would get 2 complex solutions, plus or minus square root of 2i. If that's what you're getting, no way you're going to have factors. Okay, so we leave it like this. The x plus 3, we're done there as well. All right, here we're faced with a trick, because if I know that the idea is that I'm going to want to factor by grouping, okay? And I know that because it has 4 terms. Now, the thing is, notice that the 2 and the 3, these don't have a GCF. That's a number, though they do have a letter in common. And the 8 and the 12, they do have a 4, but in general, if I take the 4 out, I'm going to be left with a number in front. I'm going to have like 2x here and 3. I don't really want that. But we could try. So let's say we pull out the GCFs, the respective GCFs. So I would have 2. Well, I can't pull out a 2 there. So if I do it as is, I get biggest power x3, 2x plus 3. And if I pull out a GCF here, I get 4. And this becomes 2x. Oh, okay, works out nicely. Other way you could do it is this. Here's how I was thinking you would do this. So we'd have 2x to the 4th plus 8x. So we rearrange because the commutative property says it doesn't matter how you add things. Okay? Then I'm going to do 3x cubed plus 12. And notice when I do this, I take out a 2x, and because these have a 2 and an x in them, and I get x cubed, because 2x times x cubed is 2x to the 4th, plus 4. Okay, then I take out a 3 as this GCF, and I get x cubed plus 4. So notice, when you rearrange, you again get the same thing on the inside. Observe that it didn't matter how I did it. I could have just done it straight out. I could have rearranged. You get the same answer in the end. You should get x cubed plus 4, and then you should get 2x plus 3. Remember, if you give me an answer with the two factors flipped around, that is 100% fine. The order of the factors does not matter because the factors are being multiplied, and we know the order of multiplication doesn't matter, okay? So you could have done it either way, but that's just getting at sometimes you might want to think about rearranging. Sometimes you'll be required to rearrange, so you have to think smarter, not harder. If it's not working out, if you can't triangulate that GCF, if you're looking at 2 and 3 and saying, I can't get a number in common, then rearrange it so you can get a number in common. All right, you gotta think, you gotta have some ingenuity there sometimes. Okay, so moving on down to the next one, we want to factor these completely. So I'm looking for a common factor. They all have a 2 in them. They all have an x in them. So I'll pull the 2x out. And now, and by the way, this can't be broken down. It's x cubed plus 4. That's 4 is not a cube, so it's not a sum of cubes. So I will leave that alone. Okay, anyway, I pull out the 2x, and remember again, no x equals. Okay, I get 2 times 2 is 4, x squared, x times x squared is x cubed, plus x, 2x times x is 2x squared, minus 6. Do I leave it? Not necessarily. So what I need to do is I look at this one, can't touch this. This one, well, I better try to factor it. Off to the side, if I do b squared minus 4ac, 1 squared minus 4 times 2 times negative 6, that would be 1 plus, 24, 48. So this would be 49, okay? And think about it. 1 is positive, telling me that this thing right here is going to have 2 zeros. So that means that factoring could be possible. Secondly, the fact that I got 49, and we know that the square root of 49 is 7, means that they're going to be 2 whole numbers, which means factoring is possible. So when in doubt, do the discriminant, okay? If you get a negative discriminant in here, if you get a negative discriminant, that means there's no zeros. No zeros means there's no factors. No factors means you're done. But in this case, I got a discriminant of positive and a discriminant, in fact, that's a perfect square. So that means that there will be 2 factors. Because if you get a whole number in the square root in the quadratic formula, when you do the square root, you are going to have numbers that are actually rational, okay? Meaning most likely factoring is possible. So what I'm going to do is I'm going to set up 2x. I'm going to do my factors. Boom, boom. So these is going to become 2x and x to get the 2x squared. Now I need to get a little creative with it. So I need to get, first of all, one of them is negative. Now, if I make this a -3, this is going to be 6. It's going to be hard to get back down to 1. So here's what I'm going to do. I think 2 and 3 is what I want. So I'm going to make this a +3 because this will be, can I get that to work? Let's see. Well, if this is 6x, no, I'm not going to be able to get back. Okay, I got it. All right, watch this. So sometimes, and you know what? You experiment, right? Okay, what if this is 2? Nice. So 2x times 2, this is 4x. Nice. Okay, so let's take a look. 2x squared plus 4x minus 3x, and 4x minus 3x is 1x. Perfect. Times 3 times -2, or -3 times 2, that is -6. So remember, when you are working with what's called a non-monic, meaning the leading term is not 1, then you got to be a little bit more careful with how you arrange things here. Up here, we could have put the 6 and 2 wherever we wanted. Didn't really matter as long as this was a 6 and this was a -2, because it's a 1 in front of there. So it didn't really matter where you put the x's. Here it does matter because you need to specifically have 2 times 1 to get the 2x squared. So it's another thing to think about. All right, so let's run through it. Can I break it down? No. Can I break it down? No. No GCF or anything? No GCF. So I'm done. All right, so moving on here, I see 4 terms. So immediately I'm going to think about what method here? I'm going to think about factoring by grouping. Okay, first, I'm going to take out a GCF. Okay, so let's take a look at this guy. So the GCF, for me, it's looking like, well, I've got a 3 in all of them. Let's go ahead and make it a -3 because I want to get the leading coefficient back to 1. Negatives are a pain to work with. And notice, if I pull out a -3, this, every single thing becomes positive. I would work with positives any day over negatives. Any day, right? Okay. They also all have an x in them. So I'll pull out an x. So step 1, GCFs come out. So this is going to be x to the third, because -3x times x to the third is -3x to the fourth, plus, because this is a negative, 2x squared, because 2x squared times -3x is -6x cubed, -6x cubed, okay, minus, we got to be careful here, so this is going to be an x because, actually it's going to be a plus because x times -3x is -3x squared, and this one is going to be plus 2. So this one is tough because it's really, really hard sometimes to factor out those negatives, and that's totally cool. All right, so now what I'm going to do is this. I'm going to go ahead and I'm going to take a look in the inside piece, okay, and here's what I see. Okay, so I'll copy my 3x down. Here's what I see. Well, okay, I see an x and a 2. I can see where the x and the 2 is going to come from. So let me take out an x squared here. And what I'm left with is x plus 2. Notice, beautiful. So what do I take out of here? Let's pop out a 1. X plus 2. Now, this is tricky because remember, every single, polynomial always has a GCF of 1. Always. Right? Because you can always multiply any polynomial by 1, and you're left with the same polynomial. It's just that might not always actually lead to anything. In this case, the GCF of 1 actually is somewhat instructive. So let's go ahead and we'll do our 3x. We'll pull out our x squared plus 1. We'll pull out our x plus 2. Okay? All right. I go back through, I do a check. Can I factor anything? Well, this cannot break down. I know this cannot break down because x squared plus 1 is not, the solutions, the roots are -I and I, so it's not going to break down. X plus 2 is done. -3x is done. So you leave it, okay? But you have to go back, because what if this is a multiple choice? Especially if it's a multiple choice. Look, x squared plus 1, if it was x squared minus 1, you're not going to see that in the breakdown, okay? You're going to see in a multiple choice, it's going to be completely broken down. So you have to be ready to really systematically attack this. All right, here we go on the last one. So first, GCFs have to come out. Are there any? 2, 3, 8, 12. Not there, but for x to the 5th, x to the 4th, x to the 3rd, x squared means that there will be a GCF with regard to the x's, and I can get an x squared out of all of them. So let's start with that. You always start with the GCF. So it's 2x cubed plus 3x squared minus 8x minus 12, okay? And basically, notice how it's almost like the same one that's up there. Okay, it's pretty similar. I see like all kinds of things that are similar there. Okay, actually the coefficients are the same essentially, but they're just rearranged. All right, so let's think about this one. Okay. So I'm gonna get a similar factorization here. But okay, so there's a couple ways you can do this. You could factor out the GCF here, and that's gonna be x squared, and then you'd get 2x plus 3. You could actually factor out the GCF here, which is 4, and you'd get the same thing. Or in this case, you have to factor out a negative 4. So what I'm going to do is, again, and when you see 4 terms, factoring by grouping has to be in your mind, okay? So biggest power of x, I can take out an x squared. So what that gives me is 2x plus 3. So over here, when I factor out that GCF, I also need to be able to have, and I'm just going to erase this to make room, 2x plus 3. Okay, so I need it to be plus, so I'm going to pull a 4, and I'm going to pull a negative 4, and the reason I pull a negative 4 is because negative 4 times positive 2x gives me negative 8x. Okay, so this needs to be a negative 4. Because again, I need to make sure this is 2x plus 3 and this is 2x plus 3. To do that, I need to have this be a negative, because if I just pull out a positive 4, it's going to be, it's not going to work out. Okay, so you have to be really careful there. This is one thing that was definitely a confusing spot for people, and so that's why we got to think about that. So here we go. X squared on the outside, then I take out the x squared minus 4, and then I take out the 2x plus 3. Okay, now I go through. In this case, I am not done, because this x squared minus 4 can be factored. So I have x squared. The x squared minus 4, we have to identify that from last year. X plus 2, minus 2, x plus 2, 2x minus 3. This x minus 2, x plus 2, you could have done that in either order, but really important, because x squared minus 4 is factorable, I have to execute on that. Okay, that's really important. Okay. All right. Lastly, factor and find the zeros. And I'll just extend this page. And of course, you'll always have access to extra paper if you need it. Okay. So I need to factor and find the zeros. So now it is an equation. So notice here, I've been saying, I don't want to know x. I don't want to know x. Okay, don't tell me x. Here, if I say find zeros, it's implied that I'm essentially solving this equation. So here, again, start with the GCF. What's the biggest thing I can get out of this? I can definitely, let's see, can I take out a 4? No, because the 4 can't come out of the 50. Let's see if I start with a 2, what it looks like. So I know I can get a 2 out of every one of them. So I have, and I can get another thing out of them. All right, so 2x, I can get a 2x squared out of everything. So it would be 12x squared minus 25x plus 12. Wow, okay. Honestly, it looks like I can't pull anything else out. So what does this tell us? 1, x could be equal to 0. Because if two things, remember, this is another question that kind of startled me. Sorry about that little alert there. That's one thing that kind of startled me that people did not know in the most recent unit. Look, guys, if two numbers multiply to get 0, one of them has to be 0, right? So if I have 2x squared multiplied by something and I'm getting 0, then 2x squared or 12x squared minus 25x plus 12 has to be 0. That is a fact. Think about it. The only way, if I multiply numbers and I get 0, the only way is one of them has to be 0. That's a fact. So that means that 2x squared could be 0, and if that was true, x would be 0. So that's done. Now I'm going to drill down into the second guy right here. 12x squared minus 25x plus 12 is 0. Okay, so a few ways to solve this. I could hit it with the quadratic formula. Completing the square would be really, really bad because x squared is positive. And so I think I'm going to... let's see if we can factor it. And if we can't factor it, we'll use my buddy, the calculator, and we'll hit it with the quadratic formula. All right. So getting 12. Now, the hard part is negative 25 is hard to multiply to, but I do have a sense that both of the numbers, the second numbers, have to be negative. And I know that because a negative times a negative is a positive, and a negative plus a negative is generally a negative. Okay, so I'm going to have a negative here. So it's just like thinking critically. All right, now the other numbers. That is going to be a challenge. Okay. So I'm thinking, what if I do 6x, let's start with 6x and 2x. So if I do 6x and 2x, there's my 12x squared. That's the only place you're getting the x squared from. Now, how do I get 25? Am I going to get lucky and get this? That would be crazy. So I'm thinking, could I do 2? If I did 2, that would be 12. So what's my options? Basically, here's what I'm getting at. What's my options for 12? I could do 4 and 3, 6 and 2, 12 and 1. Those are basically my options, or the reverse of each of those. Okay? So if I did this was 4, that would be 24. And then this would have to be 3. And 24 and 6 is not 25. Darn. What if this was 6? Well, if this was 6, then that would imply there was a greatest common factor of 6 that I haven't pulled out, and I know that that's not true. What if this was, then I don't think that's going to work. Darn. Let's see. So my other option, 12 and 1. Maybe I've got to finagle 4 and 3 somehow. Okay. So, am I missing something? That's the question. So these are ones really hard to make up on the spot. So this is a 3. If this was a 3, this would be 18. And 18 plus 4 is not 25. So is there something I'm missing here? Because there's no way to pull anything more out of that. Am I missing a factor of 12? That could be my other option. Let's see. So 4 and 3 makes 12. Right, because the idea is you have to add up to 25. Let's see. So this could be because again, the idea is if this was a 3, then I could have pulled out something. And I know if we come back and look at this, this works. This is 24x squared. This is 50x cubed. This is 24x squared, right? 24x to the 4th, etc. Okay, when you take this out of the equation, this is all that's left. Okay, and so that's something we got to work with. That's not easy to work with. Okay, so what are my other options? So I know one of them is not going to be 12, and I know that because if one of them is 12, I go way over 25. It's hard to get to 25. So, wow. Right, and again, I have to be careful here because I know that if I create any GCFs, then that means that I could have taken something out of here, potentially. But let's take a look.
Okay, so what if this was 3 and this was 4? That wouldn't work either. Darn. Okay. All right, so what this essentially means is that what I've done is I need to rethink. Sorry, I'm having some video editing issues as well. So what that means is I need to rethink what's going on here. Because if 6x and 2x is not working, what that means is I've got to try another combination. So I've got to do 4x and 3x. Again, the same way to get 12. Let's try it like this. And that's what you do. You just recycle all your options once they're done and nothing's going to possibly work, right? And the way I knew that was because I would have a nasty GCF and I know I couldn't pull that GCF out because if I could pull the GCF out here, I could pull it out here. So let's try 4x and 3x. And again, this is a negative. Oop. This is a negative. This is a negative. Okay. And so let's try this one. So again, I'll go through the combinations. And what I know is that this can't be 4 and 3 because, again, there's no GCF. So what if I make this a 3 and this a 4? So I have, there's 12x squared. There's 16 and 9. Perfect, because negative 16 minus 9 is negative 25. So perfect. So now 4x minus 3 equals 0. So x equals, you add 3, you divide by 4. 3x minus 4 equals 0. So you add 4 and you divide by 3 to get x alone. So I've got x is 4/3, x is 3/4, x is 0. Those are my 3 possible solutions, okay? That's it. Now moving on to the last problem. This is indicative of factoring by grouping. I see a 2x in all of them. Actually, rather, I see a 2x squared in all of them. So this is going to become x to the 3rd. This is going to become 3x squared. This is going to become 5x, and this is going to become minus 6. Okay. Now, this one's going to be a little bit more challenging because you've got the 5x and the 6. These don't have a number in common, so let's do a little rearrangement. So I'll keep that as is. See what my so I'm going to take, not easy. I was thinking of taking the 3 and putting it with the 6, but that's not going to work because it's going to be a 1 and a 2. Wowie. Right, because you'd think there's got to be a GCF somewhere that you can work here. Can't put the x cubed with the 6 because that's not going to really work out. Those don't really have anything in common. So what does have something in common? So we have the x cubed and the plus 3x squared. But then the issue you run into is, right, that doesn't work with the other one. Okay, if you move the 3x over, then you just get 1 and 2, right? We need to have both terms work out to be the same, okay? And whether that's possible or not, right, that's something we got to figure out. So let's just quickly double check the factoring. 2x to the 5th, 6x to the 4th, negative 10x to the cubed. There's my mistake. See, I knew I made a mistake. You know what? Happens to the best of us. All right, that explains a lot. There we go. So if anyone's tallying up my mistakes, I apologize there. All right, this makes more sense. So now let's take out an x squared on the first one, and that is going to get me x cubed plus 3. Oh, nope, just an x plus 3. And here I'm going to take out a negative 5, and that's also going to give me an x plus 3. Okay, so here's what I've got. And remember, this is going to be equal to 0. So I've got a 2x, and I'm just going to make a line here. 2x squared. I have x squared minus 5. I have x plus 3, and I got it all equal to 0. So one of the x's is going to be 0. Here, if I solve this, I get x squared equals 5. X equals plus or minus square root of 5. So x equals positive root 5. X equals negative root 5. And then here I just get x equals negative 3. So here's my 4 roots. X equals negative 3. X equals 0. X equals plus root 5. X equals minus root 5. Okay? And remember, whenever you're looking at a polynomial, the biggest power of x, 5, 4, 3, 4, 5, etc., tells you the maximum number of zeros you can have. So the fact that we're getting less than or equal to, so this is 4 zeros, this is 5, this is 3 zeros, this is 4, is a good sign. All right, so go ahead, really rewind that. I know there was a lot going on there. Please make sure you understood everything in this video section. And then in a moment, we will move on to the next set of problems. Alrighty, so we're going to go ahead and move on to the next section, and that is special factors, which is the difference of squares and cubes and quasi-quadratics, okay? So here's what I'm going to tell you. Number one, on the midterm, I will not require you to memorize sum and difference of cubes. That has always been on the wall. That will remain on the wall. You do not need to memorize that. I will preface that by saying, however, if you memorize it, it will save you time. It will. I promise you that, okay? Because you won't have to worry, you don't have to worry about all of that, okay? So, difference of squares. We should have this from last year. It's just a minus b times a plus b, okay? If that gives you a squared minus b squared. Difference of cubes. And this should be sum and difference of cubes, all right? So, here is the same. Here is opposite. And here is always positive, okay? Same, opposite, always positive, okay? That's how we talked about how to find the sum and difference of cubes. So SOAP is just an acronym for that, okay? And so by memorizing SOAP, it will help you figure that out. But if you don't, that is also okay, okay? But same, opposite, always positive may help you utilize that. So right, same sign, opposite sign, that sign's always positive, okay? Here, same, opposite, always positive, okay? And it's really just that simple with regard to that. And that's basically what SOAP means, okay? And that will remain on the board, okay? So factor completely, and again, our rules of factoring from the last part still apply. Okay, now, here we go. First, there is this one is just you can do it two ways. One, you could factor out the GCF. And then you could just, because this is x squared minus 4, and then you could do the difference of squares. Alternatively, this is 2x minus 4, 2x plus 4, and then you'd have to factor out the GCFs from each of those. I think this one's probably easier, okay? Here, so 2x is the first cube because 2 cubed is 8, x cubed is x cubed, okay? The second one is 1 because 1 cubed is 1. And it's a difference, so we use the difference rule. So same. Okay, now a squared, so 2x squared, 2 squared is 4. Opposite, so you multiply them, always positive. All right, one thing to remember is that this is not going to be factorable any further. It's not going to have any real roots. And here's how I know. B squared minus 4ac. Well, look, a is positive always. Because when you square a number, it's going to be positive or 0. And in this case, if a is 0, what are we doing? Okay, so this is always going to be a positive number. This is positive. And so basically what you have here is 4 minus 16, that's negative. And because it's negative, this is going to have a negative discriminant, and you can't factor. That is almost always, if not always, going to be the case when you do SOAP. The quadratic thing that remains is not going to be factorable. It's going to have no real zeros, though it could have imaginary or complex zeros. All right, here's a quasi-quad, and remember, there is, and I will have a video on this, and how about what I'll do is I will link right now, so take a look up to the top. I'm going to link a video to how we did this, and I recommend that you take a look at that video because that video will have information on stuff like quasi-quads, okay? So quasi-quadratics are polynomials that don't look like quadratics, but they act like them, okay? So, for example, notice the x to the fourth and the x squared, okay? So I have an x squared and I have an x squared. And when I multiply x squared times x squared, I get x to the fourth. And now, think about how could I multiply to get negative 16 and add to 6? Well, what if this was an 8 and this was a 2? A negative 8 and a 2. So this would be 16, so I get x to the fourth plus 2x squared minus 8x squared, that's negative 6x squared, minus 16. And lo and behold, this is a factorization for this polynomial, and it's called a quasi-quadratic because I just factored it just like we'd factor a quadratic, though it doesn't look like I would. Okay? Okay, so moving on down, and I'll just extend this page to have a little bit more room to work with if needed. I have 32x cubed minus 18x. So I'm thinking that I want to execute a difference of cubes, but problem, not a cube. And this one isn't either. So what I should do is let's look for a GCF. Well, I know there's an x in them, and that would be really good. What else can I get? Can't get a 4. 4 only goes into this one. Let's see, could I get a 2? Let's try a 2. 16x squared minus 9. Okay, is it a difference of cubes? No, because they're not cubes. So actually, maybe, what about a difference of squares? Well, yeah. Now, let's set up a difference of squares. So look, this is a square. This is 4x squared because 4 times 4 is 16. X times x is x squared. And this is 3 squared. That's it. And remember, with regard to the 4x minus 3 and the 4x plus 3, do that in whatever order you want. Just keep in mind that that does need to work out all right. So that one of them has to be a minus and one of them a plus. But otherwise, that's fine. All right, in the middle, again, I'm seeing a GCF. Here, it's going to be 3x. So this is going to be 8x cubed. And this is going to be 1. Now, one thing we have to work on is we always have to look for making sure there's perfect cubes. One of the big things that was tough for us when we did the quiz on factoring with difference of cubes is people didn't think that, oh man, 1 is a perfect cube. Other thing people didn't think about is I might set you up in a situation where one of them might be a perfect square and one of them might be a perfect cube. You have to know how to look at things situationally. So this is actually going to be a very similar setup to the one right above. Now, 8x cubed, well, it is a cube because 8x cubed, well, that's if I cube 2x, 2 cubed is 8, x cubed is x cubed. Remember, I can do that because they're being multiplied by each other, and b is 1. So I'm going to do this in a different color so it doesn't get mixed with that. So I've got 3x, and now here I'm going to have, nope, it needs to be an eraser. Okay. Here I need to have two x plus 1, same. Okay, here I need to have 4x squared opposite, always positive. So notice the difference here. Okay, the minus to the plus. This was a plus instead of a minus. Okay, this should have been, the sign here should have been changed. This should have been a plus. Sorry if that's not clear, because these need to be opposite. So here was a minus, here was a plus. Here was a plus, here was a minus. These were both pluses. So same, opposite, always positive. Same, opposite, always positive. Okay? Last but another quasi-quad. And so what I'm going to do here is I'm going to start by knocking out the 2. That's going to be x to the 8th, x to the 16th, right? See, don't divide the exponent. That was a mistake. That's always a mistake that people make, and that's totally cool. As you can see, I almost did that. Oh, but is there a 2 in common? No, there is not. Is there an x in common? No, there is not. So, again, this is going to be quadratic with regard to x to the 8th. Alrighty, so drop 2x to the 8ths. This is going to have to be a 2, okay? And by the way, I do need to find the zeros, and so I'm going to do that in just a minute. For those who might be wondering, when am I going to find the zeros? So that works out like that. Now, this one's going to work out a little bit nicer for me, potentially. So I know that I need 2 numbers. One of them, they're both negative, because a negative times negative is a positive, and a negative plus a negative is a negative. And I need to multiply to 12. So what I'm going to do is I'm going to make this a 4, and I'm going to make this a 3. So this is going to be -8. This is going to be -3. So see, when the number in front of the number in front of the biggest power of x in this case is a prime, it's a lot easier because there's only really one combination. Back in the previous part of this video, when I had to do a 12, and it could have been like 6 and 2, 4 and 3, 12 and 1, and another number has the same situation, it just makes it a lot harder. Okay, now I do want to look and see if they're perfect cubes. This is a cubed, this is not a cubed. This is a cubed, this is not a cubed. So we can't really break this down. Actually, this isn't even a cubed. So for finding the real and complex zeros, let's take a look. This one, let's forget about this one because we don't really have any strategies. I bet you there are. So if we want to be technical, this is like, this would be x is equal to plus or minus the 8th root of 3/2. I'm not going to ask you to do that on a test. We're not on 8th roots. That's fine. X equal to plus or minus the 8th root of 4. And I know it's the 8th root. And I know it's plus or minus because it's an even root. So if you do something times itself over and over 8 times, right? So for example, if I do, let's see if I can do this. If I can do 2 to the 8th, 256. If I do -2 to the 8th, I get 256, right? And that's how I know it's plus or minus, because when you have like an even exponent, right, the -1, that -1 next to the number that you're doing the exponent on, when it's even, right, -1 times any even power brings you back to a positive number, okay? Again, don't worry about these. Here, let's take a look. So either x could be 0 for this 2x, x could be 3/4, add 3, divide by 4, or x could be -3/4. Okay, subtract 3, divide by 4. Here, okay, x could be 0, x could be -1/2, and we need to find complex zeros, okay? So here we have 2 plus or minus the square root. This you have to do the quadratic formula. 4 minus 4ac, so 16, 4 times 4 is 16, times 1 is 1, 4ac, all over 8, it's 2a. 2 plus or minus negative 12 over 8. Negative 12, remember, square root of 12 is 2 root 3 because 12 is 4 times 3. So it's 2 plus or minus I times 2 root 3 over 8. So what we get is x. Now we have to simplify. Divide, divide, divide. So it could be 1 plus I root 3 over 4, because you have to divide. This divided by 2, this divided by 2, this divided by 2. 1 minus I root 3 over 4. Okay, so x equals 0, x equals negative a half, x equals 1 plus I root 3 over 4, or root 3I over 4. The I doesn't really matter, but just make sure the I isn't caught under the root, or 1 minus I root 3 over 4, okay? So remember, whenever you have a difference of cubes, always this is going to yield imaginary solutions, okay? All right, last piece. Factor completely and find all real or complex zeros if there is only one variable. So notice the first one, I don't want you to find the zeros. The second one, possibly. All right, so let's take a look. Here, is it a difference of cubes? Yes, this is a difference of cubes. Okay, so A, let's go back to black. So this is 3 cubed is 27. X cubed, because remember, when you cube a cube, you're going to fly high and multiply. You're going to multiply the exponents. Here, 2 cubed is 8. Y to the 4th cubed is y to the 12th. So I have same. Okay. Now, a squared, 9x to the 6th, opposite. So 3 times 2 is 6. X cubed, always positive. So that's going to be 4y to the 8th. Okay? Believe me, I'm never going to ask you to find zeros for multivariable functions. Why? Well, 1, pretty hard to do. Way out of the scope of this class. 2, there's not a unique answer, right? I could set y equal to, I don't know, 0. I could find a whole bunch, right? If y was 0, I could find a whole bunch of x's. But if y was 1, there could also be a whole bunch of x's, right? There's like infinite number of answers when I switch up the x and the y's, and I don't want to do that. We're not going to get into that. It would be cool to see you factor them. I think factoring is possible and within the realm of asking you to do, but asking you to find the zeros, I'm not going to do that, okay? Way beyond the scope of this class. All right. Here, let's try to factor out a GCF. So I definitely can see a 2, okay? And I can definitely see an x. So let's see what that looks like. There's going to be 24x to the 18th plus 43. Oop, that should be a minus 43. Minus 43x to the 9th plus 18. Wowie. All right. So this might not want to be one where we're going to be able to find it, but let's see what we got. We might not be able to honestly find all the real and complex zeros, but we'll see what happens. So I have 2x, and then this is going to be a quasi-quad. So yikes, this is quite a quasi-quadratic here. So basically what I need to do, this is an x to the 9th. This is an x to the 9th. So I need to multiply, and I might want to leave some room here because I need these to hook up to a positive number, or a 24. But then I also need to hook up an 18 somehow. So let's see. So 24, how do I get 24? So I could do 6 and 4. I could do 12 and 2. I can do 8 and 3. See if I can get any of those to work. 18, it's going to be a similar scenario, right? 18 is rough because 18 could be most likely 9 and 2. 6 and 3, 18 and 1. So let's say I go the 6 and 4 route. Okay, maybe I get lucky here. Now, I know they're both going to be negative on the second piece, and the reason I know that is because they have to multiply to a positive, which 2 negatives will, and add to a negative, which 2 negatives will. Okay, so let's see. So if I do 9 and 2, let's start with that. So it doesn't look like that's going to work, because if I do 9 here, I'm going to get 54. And if I do 2 here, that's not going to work. Okay, so that's out. What about 6 and 3? So this would be 36. And that would be 12. That's not going to work. What about if this was? Nope, because if that was a 6, there would be a GCF. So that's not going to work. 18 and 1. 18 here, ooh, that's not going to work at all, because look, 18 here, that's going to be way over. It's already going to be way over. So 18 and 1 is not going to work. So maybe I need to try a different combination. All right, it's okay. X to the 9th, X to the 9th, minus, minus. All right. What if, and bear with me here, what if I chose, what do you think I should choose? I mean, I got 2 options here. I basically could do 8 and 3 or 12 and 2. And I got to think about which ones do I want to do. And so to think about that, I want to probably choose the easier one first. Let's see. What could I do? I think I want to try maybe the 8 and the 2 or the 9 and the 3, right? It's basically a matter of thinking about, 1, which ones can I make possible, and 2, which ones are easy to do, right? Because you want to start easier first. So I'm going to do the 8 and the 3 over the 6 and the 4. 8 and 3, and let's see if I can swing this. So now I'm going to go back through it. Can I get the 9 and the 2 to work? Maybe I get lucky here. Let's see. So let's say this is 3 and this is 9. What would happen? So this would be 7. This would be, oh, no. 2. Yeah, 9 times 3 is definitely not 18. So this would be 72. Yeah, nope, that's way over. That's already not going to work. What if I do it the other way? So with the 8, I put the 9. Let's try this one out. So this would be 9 times 2 is 18. And we added 27. And let's see. Am I missing something? Oh, nope, it's not an 18, it's a 16. So a 16 plus 27, because 8 times 2 is 16. And there we go. Wonderful. There's a 43. Ah, finally. So this is the final factored form. And I think I'm going to leave it here. I'm not going to find real and complex zeros. And the reason I'm going to not do that is because in this case, I don't have any really difference of cubes. I mean, okay, so if I was going to really try to do this, 1 0 we could easily find. And believe me, I'm not going to be asking you to find zeros in this case, because this is way above where we need to be. But we do know that one of them is going to be 0 because of the GCF. I mean, we could have the 9th root of 9/8 and the 9th root of 2/3, but you know, that's something that's way above the scope of the course. I'm okay with you factoring these. This is something I might change up in the future. Okay, so again, I hope that this made sense. At least be able to please focus on factoring the sums and the difference of cubes. I think for the ones that are more straightforward, such as these, that would be realistic to find the zeros. Here we definitely can't. And these kind of maybe identify them, be able to look at them as the 8th root of it, but I don't know that I'm going to be expecting an exact answer there. All right, so please make sure, again, you understood this part of the packet, and then in a moment I will move on to the next set of problems. Alrighty, so moving on now, we're going to go ahead and come down to adding, subtracting, and multiplying polynomials, okay? So we're finally in to our investigation on polynomials, and that is moving into the next unit, right? And we kind of already have with regard to the factoring, right? Because first we did the quadratics, then we did the imaginary stuff. Now we're doing adding, subtracting, and multiplying polynomials, right? So operations with polynomials. This we did kind of at the end of September. I remember because we started this when Japanese exchange was here. So adding, subtracting, or multiplying polynomials, it's just a matter of combining like terms. That's really all you're doing here. You're just combining like terms. Okay, multiplying either requires you to either FOIL or make a box. Okay, whatever is better for you. I like to get away from FOIL because FOIL doesn't really work when you have things that are more than 3. So when we say FOIL, what FOIL is really just a method for distributing. And the problem with FOIL is that when you have more than 2 terms, you can't just do first, outside, inside, last. It doesn't really make as much sense, at least to me. So just some stuff to think about. Also here, we need to be able to identify the notation, okay? And so we'll talk about that as well. Okay, so here we go. First, we have f, g, and h as defined as follows. We need to add them. So we'll start by or subtract them. So let's start by adding f and g. So x squared plus x cubed. So notice, first you have to pick out the like terms. And we do need to write it in standard form, so from least to greatest. Okay, so what I notice is I'm going to start here. This has an x cubed. This does not. This has an x squared. The other one does not. And the order doesn't matter. So this is negative 3x plus 2x, negative 9 plus negative 7. Okay? Here, I'm going to subtract. So here the order does matter. So I'm going to do 3x squared minus 0x squared. And actually, first we have to do 0x cubed minus 1x cubed. So we have minus 1x cubed. Okay, be aware of that. 3x squared minus no x squareds is plus 3x squareds. Negative 5x minus 2x. 12 minus negative 7. Positive 19. Don't forget to do your minusing or negatives. Here's another way I would think about doing this. Stack them. And then do the columns. So 0, 3 minus 0, negative 5 minus 2, 12 minus negative 7. Okay, it's another way you can do it. And this should be a 3. It kind of looks like a 7 here, but this needs to be a 3. Okay, last one, h minus f. So 3x squared minus x squared, that's 2x squareds. Negative 5x minus negative 3x, that's like adding. So you have 2x. 12 minus negative 9, that's positive 21. Perfect. Okay? So there we go there. And I'm now moving on to the multiplication. Okay. So multiplication here, we got f times g. And this is going to be pretty tricky. I'm going to make a box. Okay. My boxes aren't great, and again, that you will hopefully make better ones because you do not have to write on a tablet. Tablets, believe it or not, are not easy to write on. Okay? All right, so now I'm going to I love the box because I just do each of the multiplications. This is the same as distributing. So I've got an x cubed here, I've got a minus 5x squared, I've got a minus 12x squared, I've got a 60x, I've got a 5x, and I've got a negative 25. So let's look at this. I've got an x cubed, I've got a negative 17x squared, I've got a 65x, and I got a minus 25. Okay, so x cubed minus 17x squared plus 65x. Make sure we look at that as an x minus 25. All right, f of x squared just simply means to take f of x and to multiply it by itself. So I have x minus 5, x minus 5. So that's x squared minus 5x minus another 5x plus 25. Okay, so that's x squared minus 10x plus 25. Okay, that is more of a review of freshman year. We do need to know how to do those from freshman year. Lastly, and this is going to be a doozy, we need to make a really big box because we're multiplying a trinomial, which is a 3-termed polynomial, times another one. So this is going to require a lot of multiplication, and that's why I like the box, because it keeps it very organized. The order doesn't matter, so I'm going to stick x squared minus 12x plus 5. You could do it the other way if you wanted to. 2x cubed, 4x, and negative 9. Okay, so here we go. I'll do the innards in red. So we have 2x to the 5th minus 24x to the 4th plus 10x cubed. Okay, this is 8x cubed minus 48x squared plus 20x. This is negative 9x squared. Now, 12 times 9, we'll just calculate. We'll just use our friend Mr. Calculator here. 108. And I did positives because a positive times a positive is going to have the same sign as a negative times a negative. Wow. Okay. So I'm going to actually draw a line and continue this down here because I can just make some space here. So what do I have? I've got, and I'll write this. It's tough to write on the side, so I'm going to write a bunch. I'm going to kind of be writing a bunch of things. So 2x to the 5th. Okay, now x to the 4th. There's only one of those boxes. X to the x cubes. I've got 10x cubed here and another 8x cubed there. So that's 18x cubed. And I check it off as I go so I know I'm good. And now I have negative 48 minus 9. That would be negative 57x squared. Then I have 128 x's. And then minus 45, okay? So if you can keep things nice and organized, that will make this a lot easier for you. And the box is really, really efficient at helping you do that. Okay, on to the last one. Write the equation of a polynomial in standard form that has the following. X-intercepts at these 3 points, points up positive directions on the end, both directions. So that's the tricky, and has a positive y-intercept. Okay, so let's start with this. We know it's got to look like, getting a little ahead of myself there. It's got to start like this. Let's do this in black. So we know it's got to start like this. Got to have x minus 2, x minus 3, x plus 5. That locks in the intercepts. But here's the problem. Okay, this is a cubic as is because there's 3 x-intercepts, right? And if I FOIL this, I'm going to have to do the biggest power of x is going to come from x times x times x. This is not going to work. So I'm going to have to somehow think about how to make this point up in both directions. So if I was to graph this, it's going to come down here. Then it's going to come up at the 2 and back down at the 3. So this is a problem for 2 reasons. One, it's going to have a negative x-intercept. and 2, it's going to go down in both directions. So here's how I remedy this problem. I make this a squared. Okay, now it's going to point in the same direction, except here's what it's going to look like. Remember, in this case, it's going to bounce, go through, go through. Okay, because remember, it bounces when you have what's called an even multiplicity, and it goes through when you have what's called an odd multiplicity. Okay, so that's what this graph's going to look like. The fact that the a value, leading coefficient, is 1 is going to ensure that it goes up. And what you call the a value doesn't matter, because what's more important is the fact that it points up. Okay, I'm going to make it 1 because if I don't have it, if I get to choose, I'm just going to choose the easiest so I don't have to do the distribution at the end. All right. So here's what I'm going to do. I'm going to multiply out x minus 2 and x minus 3. That's x squared minus 5x plus 6. Okay. Here I'm going to do this out. This is just my choice. And then I'm going to just multiply those two together. Okay. And you can already see I'm going to end up with a quartic. And quartics always point in the same direction on the ends because they're even degree polynomials. X squared minus 5x plus 6, x squared 10x 25. Okay, so this is x to the 4th. This is negative 5x to the cubed. This is 6x squared. This is 10x cubed. This is negative 50x squared. This is 60x. This is 25x squareds. This is negative 125x. This is 150. Okay, 25 times 6, right? 25 times 4 is 100, and then another 50. All right, so we combine them. Let's do it really quick. Let's see if I can use my smart notebook skills here. Let's see what's going to happen. Beautiful. Oh, Mr. Moray, you've got this. All right, x to the 4th. Okay, plus 5x cubed. Now, this one's going to be tough. I've got 3x squared terms. So negative 50 plus 25 is negative 25 plus another 6. And you could use your calc for this as well, right? Right, that's fine with me. And then add these up. So negative 125 plus 60 would be negative 65, because 125 minus 60 is right. And we can also, again, check this. 125, I'll just do 125 minus 60. And that would be 65. And so it's the opposite of that, because 125 is the negative 1. And then finally, 150. Okay, so we're assembling our polynomial by 1, starting by setting these up, because when you see intercept, you want to think factored or intercept form. So those 3 terms force the intercepts. Positive y-intercept, we needed the bounce at the minus 5. And remember, if I made either of the other ones bounce, it would have still gone up, but you would not have had the positive y-intercept, okay? And then again, keeping a 1 points it up. Now, if I had tried to get cute with it and made this a 2 or a 3, then I would have just had to go through and then distribute that a value here. Again, I chose 1 because if it's about doing more or less work when I don't need to, in this case, I'd rather do a little bit less work, because the idea is to get it to be that, okay? And so again, since we know that this factors into this, we know this is going to have 1, these x-intercepts, because they're equivalent. They're equivalent, so they have to have the same graph. 3 x-intercepts at specifically those 3 points. We know that it is going to point up in both directions because the a value is positive. So we're going to have positive end behavior, positive infinity end behavior on both ends. It's got a positive y-intercept because, again, it's going to bounce at 5, hit a positive, come down, go through 2, go through 3. Okay, so it hits all 3 of these things. Okay, so I hope this made sense. If not, please go back and go through this and make sure you understand every single piece of this. And then in a second, I am going to move on to the next set of problems. All right, let's keep it going. Thanks for your persistence. We're going to go ahead and move on to dividing polynomials. Definitely not an easy topic. And so we'll definitely dive into these ones head first and see what happens, okay? So 3 ways to divide polynomials. One is, okay, polynomial long division, traditional method. Second is the box method, which is like a puzzle, so it's like the reverse box method. And the third is synthetic division. Okay, so that is the 3 methods to do it. The remainder theorem says that when you divide f of x by x minus a, the remainder is the same thing as plugging a into the function, and so that's why sometimes synthetic division is can be used to do what's called synthetic substitution. And finally, the factor theorem says that if f of a is equal to 0, then the remainder is 0, right? So f of a is a remainder when you divide by x minus a. And if f of a is 0, the remainder when you divide by x minus a is 0. And if the remainder is 0, then x minus a is a factor of f of x. And so this factor theorem is a result of the remainder theorem. All right, and so we call it, I believe in class, a corollary. Okay, so let's start by doing some division. I'm going to show you a couple different ways. I'm going to avoid using polynomial long division. The reason I'm going to do that is because, in my opinion, I'm going to try, but I find that polynomial long division is very difficult to execute. If you make any mistakes, it's really easy to just mess everything up and then have everything be messed up after that. I'm going to do this. I'm going to recommend synthetic division when the thing you're dividing by has a leading coefficient of 1, or the box in that case. Okay, so one of those two. So up here, I'm going to show you 1, a synthetic problem, and 2, I'm going to show you a box problem. So let's do synthetic. So first, I set up 5 because that's what makes the right-hand term, the thing you're dividing by, 0. Here I'm going to put my coefficients. Okay, p to the third, p to the second, p, nada. Okay, so again, I bring it down. 1, multiply by 5, 5, add through, -5. Okay, you add them through. This is going to be -25. Add them through, -5. Multiply by 5, -25. Add them through, 1. Let's see what happens when I plug this in. So if I plug in 5, right, I'd get 125, okay, minus 10 times 25 plus, I know 20 times 5 is 100, plus, notice that when I plug in 5, I get 1. When I divide by, p minus 5, get a remainder of 1, okay? So how do we write this? So again, this is our remainder, so that's minus 5, that's minus 5p, that's p squared. So p squared minus 5p minus 5, and actually, technically, I do need to add 1 over p minus 5. Remember, that's how we write the remainder. Okay, that's with the bus. Here I'm going to box this one. So to box it, I'm going to write n and 2. Now, here's what we need to remember. when you have this polynomial and I'm dividing by this polynomial, the degree of the remainder, the highest power of the remainder, is essentially going to be this minus this, okay? And if you think about it, we know that this polynomial times this polynomial will equal this polynomial, okay? So in other words, if I take p minus 5 and multiply by p squared minus 5p minus 5, and then add 1, I'm going to get this. And remember, the biggest power of the answer comes from the biggest power of one thing and the biggest power of the other thing. Sorry about that little pop-up there, okay? So basically, what does that tell me? That tells me that what I need to do is I need to ensure that when the biggest power of my answer needs to be 2, because when I remultiply n squared times n, that's going to give me my n cubed. So you could use that to inform your boxes, or you could leave it open. Your choice. So look, this needs to be n squared because n squared times n is n cubed. Okay, this needs to be, then this would make that 2n squared. So this would be 2n squared. I need 7n squared. So this needs to be 5n squared. So these add up to 7. Okay, but if this is 5n squared, well, then this would be 5n. Okay, but if this is 5n, this is going to be 10n. And I need 14n, so that means this is going to be 4n. All right, but if this is 4n, this is 4. But if this is 4, 4 times 2 is 8. Now I have 8, right? But I want 3 in my answer. So that means I need a remainder of -5, right? And if you think about it, I have 3. The difference between what is supposed to be there and what I get in my final box is -5. Okay, so let's take a look and see what happens here. So if I plug in -2, because this is a positive 2, if I plug in -2, I get -8 plus 14, or rather, nope, plus 28, because it's 4 minus 28 plus 3. Well, we can see the 28s are going to cancel. Beautiful, and I get a -5. So you don't have to do that, but that's just a cool check. So my final answer, n squared plus 5n plus 4 plus -5 over n plus 2. That's how you write your final answer. All right. Okay, so now I'm going to do a little bit more division down here. So synthetic, no, do not synthetic this guy. Why? Because this leading term, I don't like this. I'm going to try at my own risk to box this. I do not want to go for, I'd really, really, really not like to do traditional. I really am not a fan of it personally. 2p minus 7. Okay, so here I need a 2p squared. If that's going to be the case, this needs to be a 2p. Oh, nope, not a 2p. 2p or not 2p? P. 2p times 2p equals 2p squared. Okay, but if that's p, this is -7p. Okay? But if this is -7p, well, this has to be 14p because I want 7p in my answer. So that makes this needing to be 7p to get that. Oh, nope, not 7p. Just 7, if that's going to be the case. And if this is -7, if that's 7, this is -7, I get 49. And so actually I'm done. I cannot go further. Right? Because that's it. Once you get to a constant, you're not going any further. So what I get is I get a remainder of 10. Okay? And what that means is this. That means that I have p plus 7, okay, plus 10 over 2p minus 7, okay? Here, let's do a synthetic. So remember, I do the -3. Now, remember, be careful. This is not in standard form. Okay? set up my little wheel. We got the bus. Okay, bring down the 1. 1 times -3, -3. This is adding to get -7. This would give me 21. Adding would give me -9. Multiplying again would give me 27. The result is 9. So my final answer, k squared minus 7k minus 9 plus 9 over 3 plus k, or k plus 3, your choice. Okay, lastly, you know what? Heck, we'll synthetic this one too. Okay, remember, the key with synthetic, you have to remember that you cannot forget to leave out. So that's a 1x squared, 0 x's, and -74. Remember, that's the biggest mistake people make. So I bring down the 1, multiply by 8, I get 8. Add through the 8, I get 8. This is 64, -10. So what I get is x plus 8 plus -10 over x minus 8. And if you think about it, x squared times 8, x plus 8 times x minus 8 is x squared minus 64. I subtract a 10, I get -6, I get -74. Okay, finally, determine if d of x is a factor of f of x. So 2 ways I could do it. 1, straight up plug in. So for example, I plug in -2, boom, boom, boom. I'm going to figure that out. So for example, 3 times 16 plus 7 times -8, because that's -2 cubed, plus 3 times 4 plus 2, because it's minus -2, minus 4. I get 2, so it's not a factor. Other way I could do it, do quick synthetic. So 4, 3, 2, 1, 0. Bring down the 3. Bring down the 3. 3 times -2, -6. This is a 1. It's a -2. That's a 1. That's a -2. That is a -3. That is a 6. That is a 2. So nope, not a factor. Not factor because the remainder should be 0. Over here, let's try the same thing. So I plug in 2. I get 3 times 2 is 6. 2 to the 4th is 16. So again, I'm going to get 48 minus. Okay, so that's going to be 248. So it's going to be minus 24. Okay, minus 24, 36, plus 10, minus 2. Let's see what I get here. -4. So it's not a factor there either. Okay, again, let's try the synthetic to back it up. 4, 3, 2, 1, 0. Set the remainder. Bring down the 3. 3 times 2 is 6. Add them, you get 3. Multiply, you get 6. Add them, you get -3. Multiply them, you get -6. Add them, you get -1. Multiply, you get this. Add them, you get -4. So not factor. It's not a factor. Okay? So again, this is just straight through multiplying, dividing, making sense of those operations. Please make sure you understand these methods. I'm not going to recap long division here. If you want long division recapped, you need to see me outside of class. I would love and be happy to do that. Right now, though, in this, I'm emphasizing when you have a coefficient, leading coefficient of 1 in your factor, you need to make sure that you use the method of synthetic division. Okay, otherwise you're going to use the box. We may see examples of when you have an x squared that's being divided, but for now, we're just going to stick with these kinds of terms. So again, please make sure you understood this. Take your time to rewind if needed, and then in a moment, I will move on to the next set of problems. Alrighty, so we are going to go ahead and move on, and let's take a look at what we got now. Ooh, solving polynomial equations. I love this. Okay, so generally when solving a polynomial, you want to make one side equal to 0. That is generally the case with polynomials whose degree is more than 2. Your primary strategy needs to be factoring. That's what I believe, because there's no way to really do this easily. We don't have any direct equation, whether that be grouping, etc. Once you get down to a quadratic factor, you could use the quadratic formula. You could also complete the square, etc. I would caution you to avoid using the quadratic formula if you could factor instead. However, when I ask you to solve at this point in the game, when I ask you to solve a polynomial, I do expect you to include any complex number solutions. Okay, so here we go. Let's jump right in to the first one. And what we want to do is start by looking through, are there any GCFs? There are. The GCF is 2n. So I'll put an n squared plus 12n minus 28. Okay, I could use the quadratic formula. I'd actually rather not. Let's see if I can get away with it, and it looks like I can. So what I'll do here is I will do n plus 14 and n minus 2. And so that gives me n is 0, n is negative 14, n is 2. Okay. All right, next one. This is actually a difference of squares, but I'm going to go ahead and pull out a 4r. So basically what I'm going to do is I'm going to go ahead and I'm going to factor out the, let's see, make that an r cubed. And I got to do 64 divided by 4. Let's just get lazy with it. Let's get lazy with it. I'm sure I could do this in my head. 16. What a cop out. 16. And actually, I could get one better on this one. I can actually pull out an r squared. So I'm actually going to pull out an r squared, and that's going to make this r squared, and I can lock that in as 16. And now what I'm going to do is it's going to become a 4r squared, r minus 4, r plus 4, because it's the difference of squares. So this becomes r is 0, r is 4, r is negative 4. Okay, those are my 3. Coming down here, I'm noticing a little bit of an issue here. I believe what happened is one of these somehow ended up down here. So that's kind of awkward. So let's forget about this one. I'll switch that for next year. Here, I do want to get one side equal to 0. So I'm going to combine. So I should get 3r cubed. I'm going to subtract the 5r's out of here. So I'll leave 3r squared. And then I'll minus out the 9r. So you do want to make it equal to 0 generally. Okay? Because with the quadratic formula, it has to be equal to 0. With factoring, it's useless if it's not. All right, someone asked me, hey, Mr. Moray, can I make it factors equal to 1? Yeah, sure, but then you're going to have to play around and get the numbers to be equal to 1. You don't know what the numbers are. If it's equal to 0, you know one of them is equal to 0 for a fact. Okay, so it makes it easier for you. Okay, now, GCF, we hit a GCF, so I've got a 3r coming out. I've got an r squared. 3r times r squared is 3r cubed. I've got a r, and I've got a minus 3. Okay. So here, let's take a look. I can't multiply to 3 and add to negative 3 and add to 1 because 3 is only 3 and 1. So I'm going to have to execute on the quadratic formula. So first of all, this is r equals 0. Then over here, I've got negative 1 plus or minus the square roots of 1 squared plus 12, because 4 times 1 times 3. but it's a negative 3, so it becomes an adding of 12 over 2. Okay, so basically what I get, r equals negative 1 plus the square root of 13 over 2, r equals negative 1 minus the square root of 13 over 2, and 13 is prime, so it can't be broken down any further. Okay, coming on down here, again, we do want to make it equal to 0. Let's just quickly extend my page. So I'm going to subtract the 2x, so 3x cubed plus 2x squared minus 2x. Let's pull the GCF. So again, this is giving us x is 0. What we're going to get here is on the bottom, should I go to factor? Let's try, right? It's always worth it to try to factor if you can. I know that factoring is possible because b squared, if this is a negative, then b squared minus 4ac will be positive. All right, and if b squared minus 4ac is positive, then there could be at least 2 real factors. Okay. So if I do that, it's going to have to be a 3 and a 1, 3x squared. This is going to give me, could I get a 2? I feel like I could. Well, the only way to get negative 2 is to do negative 1 and 2. I feel like I can get it. No, can I? Well, let's see. If this is negative 1 and this is 2, 6 minus 1 is not 2. Okay, if this is negative 1 and this is 2, negative 3, no, it's not going to work. Darn. Okay, no worries. We'll just use the quadratic formula. It's always worth to try. Okay, negative b plus or minus the square root of b squared. This is going to become a plus. 4 times 3 is 12. 24 all over 2a, which is 6. So this is 16 plus 24. $40. Okay, 40. 40 is 4 times 10, so it's 2 root 10. Divided out, because you got to simplify. Negative 1 plus or minus root 10 over 3. So when we get x is root 1 plus, negative 1 plus root 10 over 3, minus root 10 over 3. Okay. Lastly, let's just swing over here. So on this side, what we're looking at is x to the cubed plus x squared. Let's minus that out. Let's minus that out. This one looks like we want to use a factoring by grouping. Okay. I don't know if that's possible though. Let's see. Well, let's see. I don't know if we can. Because if I slide over, oh, yes I can. I just got too excited. There we go. Yes I can. I was going to say. All right, so now I've got x squared plus 4 and x plus 1 equals 0. So this is straight up x equals negative 1. This is x squared equals 4. So x squared equals negative 4. So x equals plus or minus the square root of negative 4, which is 2i. So I've got x is 2i, x is negative 2i, or x is -1. So remember, you have to include imaginary solutions. Notice how the sum of all the solutions we have, not the sum, or rather the total number. If I sum the number of solutions to here and here, I get 3, right? And remember, the number of total solutions has to be no greater than the biggest power of x, in other words, the degree. And remember, here we want to include imaginary or complex solutions if they exist. All right, so please make sure you understood what I did here in this video, and then in a second I will move on to the next set of problems. Here we go. Graphing polynomial functions. This one's a tough one. You may want to use your calculator for this, and this is why I've got the calculator ready to go. Okay? So, Mr. Murray's secret, what's my secret? Is you always make a table. This is on my board. It's been on my board for a while. Okay? Okay? So, in your graph, or rather, not in your graph, in your table, when you make a table, some easy points to include: the y-intercept, because you're plugging in zeros. Any x-intercepts, if you can find them. And you may have to either execute on the rational root theorem, or you might have to execute on factoring, if you can. A large positive and a large negative number defines the end behavior, and any other points you think might be helpful. All right, so let's go ahead and take a look at this first one here. All right, and what I have is I've got x cubed minus 4x squared plus x plus 6. Okay, so here's my table, x and y. Now, I know that the factors of -6 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Those are the factors of 6. Okay, and so what I'm going to do is I'm going to actually insert a new page here. Okay, and I'm going to do plus or minus. I'm going to make my synthetic division table. Okay, I'm going. My pen's going kind of nuts right now. All right, here we go. Try this again. All righty, this is a better table. Okay. So my polynomial is x cubed minus 4x squared plus x plus 6. Okay. And you'd have like a lot of paper on the midterm to do this. So I've got 6, which means, again, I've got plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Okay, so what I'm going to do is, okay, I'm going to start by plugging in 1. Okay, so what that means is that if 1 makes this 0, then x minus 1 has got to be a factor. So let's bring it down. So 1 comes down, we get 1. Okay, 1 times 1 is 1. 1 plus 4 is -3. Okay, -3 times 1 is -3. That's -2. -2 times 1 is -2. And that, when I add it to 6, would give me, I believe, 4, which is not 0. So 1 is out. Now I'm going to do, let's try -1. So the 1 comes down again. That's -5 when I do that. Okay, -5 times 1 is 5. 1 plus 5 is 6. And that should give me 0. So let's just check to make sure. So it seems like -1 will work. Let's just check that. So I've got -1, okay, minus 4, because -1 squared is 1, minus 1 plus 6. Okay, so -1 is a factor. So that means that so far, what my polynomial looks like is x plus 1, and remember, this is the rational roots theorem, times x squared minus 5x plus 6. And now I'm going to factor the second one, because what the heck is the point of rational roots theoreming the second one? The good news is, right, 1 and -1 are out. But if these are factors of this original, then they've also got to be factors of this. So that actually helps me, because now I've got a set of candidates to use on this one. Okay? So these are x's, and I'm going to say this is minus 3 and minus 2. So my roots are -1, -3, or positive 3, and 2. So I'll come back here, -1, 3, 2. Notice the multiplicities are all 0, so they are going to bounce. Okay. I also am going to choose 0, get my y-intercept, and that's going to be an easy 6. We can see that right away. I'm going to go positive. So let's say I choose positive 10. Let's do this on my calculator. I get 1,000 minus 400, because 10 squared is 100, plus 10 plus 6. So that's 616. Remember, I do that because that tells me that as x is getting big, y is getting big. Now I'm going to do the opposite. I'm going to choose -10. So negative 10 cubed is -1,000 minus another 400, because -10 times 10, -10 is positive 100, minus 10 plus 6. Okay, and we get -1404. And you can see that the majority of the value comes from the whatever is being cubed. The biggest power of x always contributes the biggest part of the value. Okay, so here I go. I've got -1, 0. I've got 2, 0. I've got 3, 0. I've got 0, 1, 2, 3, 4, 5, 6. So if I'm asking you to do just a rough graph, here's what we want to see. Coming up, hitting the y-intercept. Coming down, even odd multiplicity. Okay, it's going to come through, come back, and this is what we get. Does not have to be a Picasso, but this is more or less what it needs to look like. Okay, now what we want to do is we want to do some analysis here. So we have the zeros, -1, 0, 2, 0, 3, 0. Okay, we know those. End behavior. Okay, so the limit as x goes to infinity is equal to infinity. The limit as x goes to -infinity is -infinity. Or in other words, as x goes to infinity, f of x goes to infinity. As x goes to -infinity, f of x goes to -infinity. Either one of those notations works. Okay. Increasing, decreasing. Ooh. Let's do the local min and max first before we figure that out. So we're going to go to our y equals. Let's clear out all of our y equals. So in this case, in these kinds of problems, you would be allowed to, if I was asking you to only graph, I'm going to expect you to be able to do that without the use of a calculator because the rational roots theorem is in play. If I ask for things like extrema, like in this case, you would need to actually use a calculator, or otherwise I would make it such that you could do it without the use of a calculator. Most likely you're going to get a calculator in these kind of problems. So I'm going to go ahead and plug that in. Let's graph it. Oh, beautiful, beautiful. Now, I believe there are calculations for minimum and maximum. So let's go. So left bound on the min. Remember, we do the minimum function, left bound on the min. Put a right bound on the min. Guess? I don't know. Oh, that's weird. That is not what we should get on that one. See, so what I'm looking for is the absolute minimum. Why are we not getting the right minimum? Let's try it one more time and see what we can do. So here's the left bound on the min. Max. The right. Oh, we want to do it's asking me for a minimum. Okay. Here's the right bound on the min. Let's take a guess at the min. All right, here's a minimum. So first of all, there is no absolute max or min, and I know that because it points to positive and negative infinity, so there's going to be no one point. The min, we do have a local min. So min, a local min, and our calculator tells us it's, now we're going to round to 3 decimal places, 2.535, comma, negative 0.879. That's a local min. Now let's do a local max. We're going to use our maximum function. So that's calc 4. Okay. Left bound. I think I bet I had my functions mixed up before, and that's why it was giving me that error. Get a healthy right bound. So remember, it's going to calculate all the maxima in this bound. Maximum locked in. So I come back. Maxima 0.131, comma 6.065. Perfect. Okay. Now I'm going to come down, increasing, decreasing. So here's why we have to know this. So I'm increasing in two places, negative infinity to 0.131 and 2.535 to infinity. I'm decreasing in one place, and that's 0.131 to 2.535. Okay? And you need the min and max because the min and max are the cutoff between where you're increasing and where you're decreasing. So I really encourage you to go back and make sure you understand what I did there. And I'm going to definitely right now move on. So please make sure you rewind if that's what you need to do. Okay, no double black diamond on this one because I feel like there's already so much going on with what we have now. But we are going to go ahead and try to execute on this one right here. So, all right, here we go. What I'm going to do is I'm going to hit the same thing with the rational roots. And so what I'm going to do here is I'm going to pop to my next page. Okay, and what I have is, all right, and it always wants to zoom to the top on me. All right, negative x to the fourth plus x to the third. Come on now. Plus x to the third plus 7x squared minus 13x plus 6. Son of a... Okay, so here's what I do. Box it. Make a nice long box. Okay. X cubed. 7x squared. Okay. So here's my negative 1, 1, 7, negative 13, 6. Okay. Now, factors of 6, we know that. 1, 2, 3, 6. So, and I know I'm making this a little bit sloppy, and that's because it's kind of difficult for me, again, being on a tablet. So, look, I'm going to go for the 1 and the negative 1. Heck, it just might work. Okay? Before I do that, though, I am going to do this. I am going to go ahead... yeah, I think I am going to do this. I'm finding the zeros right now. So what I'm going to do is I'm going to factor out a negative 1. So I'm going to go x to the fourth plus, minus x cubed minus 7x squared plus 13x minus 6. It doesn't change the factors, but what I'll do is I'll just flip these signs. 1, negative 1, negative 1, positive 1, negative 1. Okay? Just makes it easier for me to have the leading term be 1. Okay? It doesn't matter. The zeros are going to be the same because, look, if it makes this 0, what's negative 0 is 0. Okay? So it won't matter there. Okay? So I'll bring down the positive 1. Positive 1, that becomes a 0. 1 times 1 is 1, plus 1 is 0. Plus negative 1 is 0. This stays a negative 7, right? Negative 7 times 1 is negative 7. That becomes a 6. 6 times 1 is 6, so that should be a 0. So let's just check that real quick just to make sure we're right. Okay, so 1's easy to plug in. 1 minus 1 minus 7 plus 13 minus 6, 0. Beautiful. So that means x minus 1 is, in fact, a factor of this guy. So what I have is, I have minus x minus 1. Then I have x cubed plus 0x squared minus 7x plus 6. Okay, and then we do it again. So now I have 1, negative 7, and 6. Boom, boom. I'm going to try it again. Look, 6 factors. 1, 3, 2, 6. So we'll try 1 and negative 1. Okay? So what that means, let's bring down the 1. We get 1. 1 times 1 is 7. 7 plus 1 is 7. 1 plus negative 7 is negative 6. And it should be 0. And see how I know this? Look. 1 minus 7 is negative 7. Plus 6 is 0. So what this means is, I come down again. And this is going to be in this case, but here's the big mistake we made. Here's the big mistake that I just made with synthetic division tables. Oh no. What did I forget, folks? I forgot to include the 0. Okay, we got to double check this because the 0 does need to be included. Okay, so let's go back. Okay, hopefully you guys caught that. So here's what I mean. Good thing I did that before moving on. So you got to have the 1 for the x cubed, but it's synthetic. So the fact that there's a 0 there matters. Now I know the 1 is going to work from having plugged it in. I know personally because it's not going to affect anything, right? I visually did 1 minus 7 plus 6, but we should make sure it's mathematically correct. So bring down the 1, that becomes a 1. That becomes a negative 6. That becomes a 0, right? Because bring down the 1, 1 times 1 is 1, 0 plus 1 is 1, 1 times 1 is 1, negative 7 plus 1 is negative 6, negative 6 times 1 is negative 6, negative 6 plus 6 is 0. So, same result, but we should be mathematically precise here. Because what remains does matter. X squared plus x minus 6. All right, so now we're going to try to factor the last one, and that should be doable. And so we have x plus 3x minus 2. Okay, so the final polynomial equivalent minus x minus 1 squared, x plus 3, x minus 2. So our zeros are 1, negative 3, and 2. Let's come back. So make our t-table, x, y, 1, negative 3, and 2. Remember, this has a multiplicity of 2, so it's going to be a bouncer. Okay, 0 again hits a 6. We know that this is going to be pointing down in both directions because it's got a negative leading coefficient. We know that, and by the way, if I'm asking you to graph, I do want to see this table done. You can't just graph it and guesstimate it, right? The graph can be good for filling in some of these, but not everything. Okay, so let's plug in, let's bang out a 10. So I have 10 to the fourth plus, well, I know 10 squared is 1,000. Oop, be careful. Make sure you hit that to bring it down. Plus 1,000 plus 700 minus 130 plus 6. All right, big number, but I actually made a mistake there because this has to be, see, I got to get it all the way over, darn it. Hopefully I've hit it enough times. All right, second, insert. There we go. All right, so positive 10 gives me negative 8424, meaning I'm pointing down on that side. And now what we're going to do is let's do a negative 10. So I've got negative negative 10 to the fourth, plus, and then I'm going to minus 1,000 because I know that negative 10 cubed is negative 1,000. This isn't going to make a difference because negative 10 times 10 is still 700. Now that's going to become a positive 130 because the negative times a negative. But it doesn't really matter because just this part alone really pulls it in there. Okay, so that's indicating negative end behavior in both directions. So let's start this out. Negative 3, 1, and 2. 1, 2, 3, 4, 5, 6. Okay, so start coming down. Come up. All right, here we're going to bounce and then go through. Okay, why are we going to bounce? Because remember, it's x minus, so this one was minus x minus 1 squared. That's the bounce. X plus 2, x plus 3. Now look, I'm not looking for, x minus 2, x plus 3. Look, I'm not looking for a Picasso here, okay? It doesn't have to be a Picasso. It just has to be mathematically accurate, okay? So mine wasn't great, again, because I'm on a tablet. All right. So here, let's clear it out, and hopefully this agrees. So I've got x, or negative x to the fourth plus x cubed plus 7x squared minus 13x plus 6. Okay, checks out. Let's graph it. And here we go. See what the graph looks like. Woo, way out there. All right, well, good news is our intercepts are working out nicely. I am gonna see if I can do a zoom fit. See if that helps. Let's try a zoom fit. And hopefully that will fit to the graph. Darn. Not as nice. It does not as nice as I want it to be. So here's what we're gonna have to do. We're gonna have to manually set the window. So it's just a little bit too small. I think the x's are fine. So I'm going to set the y. I'm going to reset the y min. So let's clear the y min out. And notice how it had a good sense of what was going on, right? It set it's a negative 10. So what I'm going to do is I'm going to set the y min. I don't really care. I already know what's happening there. So I'll set the y min to maybe negative 5. And I'll set the y max to maybe 20 and see what happens. And you're just going to basically play around with the numbers. At this point, it doesn't really matter. I'm only using the graph to figure out for me basically the mins and the maxes. So again, that was too small. I'll set the y max to 30, graph it again. Still a bit too small, but I'm getting there. Set the y max. We got to be careful when you set the y max. Okay, so maybe I'll set the y max to 50, 50, graph it again. There we go. Beautiful. Okay, so I am going to reset the view once I get the first max. Again, there is going to be an absolute max, so we do want to make note of that. So again, second, trace to get calc. I'm going to start with the maximum, and I, again, am going to reset the window once I've calculated the maximum. So the left bound, we need to come past it on the left. A healthy distance, hit it. Come on the right, hit it, take a good guess, boom. And we have a maximum, okay, local, so we have a max, one max, we have at least one max. I can see we're probably going to have two, okay. And again, notice how that reveals like a potential inaccuracy here, right? We know it's really going to come up and then come down. Okay, that's okay. Your graph, that's okay. I'm not going to be super picky about that. I want to, because again, the graph shows the y-intercept, the x-intercepts, and as you can tell from the video, I didn't know that before I made the graph, okay? So negative 1.932, 36.100. Adding the 00 does matter because that's telling me No, Mr. Moran, I didn't round that. There really were zeros there. That's important. Okay? That's a max. Okay, so what I'm going to do is I'm going to hit zoom 6 to reset the window. And I don't really care about that number anymore. Now I want to look at this right here. And I'm going to now do, nope, go back to my graph. Nope, not table. Though the table could be helpful. Turn off second. Come on. Let's go back to the graph. So I'm going to do second, calc. I'm going to do, I can see there's another max. So let's go ahead and hit 4. And see it says calc maximum. So I'm going to get, make sure I'm down here. Left bound of that local max. Right bound of the local max. Guess the local max. Ooh, good. Nice. So there's 2 maxes. So I'm going to write and, like ampersand, or you can just write the word and. 1.682, comma, 0.693, because I have to round that, okay? Min. Okay, there is a local min, so we're going to calc the min. So that's option 3. Go to the left of it. Go to the right of it. That should be good. Oh, nice. So the minimum in this case is going to be, and that we should have been able to figure out 1, 0. How do I know that? Because it bounced off and went back up. Okay, so it is, and if you see this, okay, what is this? This is technically 0.11 zeros and a 3. That's 0. Okay, that we're going to call that a 0. Okay, so absolute max. There is one absolute max, and it is that highest point up here. Okay, it's the local max, negative 1.932, 36, not 63. Just had a little bit of flippity-doo there. 36.100. So that's the absolute max. Increasing and decreasing. So we know it's increasing from negative infinity to negative 1.932. And it decreases, then it increases from 1 to 1.682. Remember, you're using only x's here. Decreasing. Okay, it's decreasing from negative 1.932 to 1. And then from 1.682 to infinity. Okay? It's again all based around the max and the mins. End behavior. The limit as x approaches infinity is equal to negative infinity, or as x goes to infinity, f of x goes to a negative infinity, and the limit as x goes to negative infinity is also negative infinity. Finally, zeros, 1, 0, negative 3, 0, 2, 0. Okay, so a lengthy explanation. What we need to get out of here is a few things. Using the rational roots theorem, again, taking the factors of the constant term, plugging them in, and then using that to factor. 1, 2, plugging into a calculator the function. 3, using the 2 calculator functions by doing second calc, minimum, maximum, to accurately, to 3 decimal places, calculate local maxes, local mins, and then interpreting to see if any of those local mins are also absolute mins. The increasing, decreasing, and end behavior are review from last year. The only thing we're going to kind of spice it up this year is by also throwing in there that they're not going to always be nice numbers and as clean as they might have been in the past. Okay, so again, please make sure you understand what we did in this video, and then in a moment I am going to go ahead and move on to the next set of problems. All right, wow, so here we are in the next set of problems. I'm just going to quit out of here. Here we are in the next set of problems. This is regression, okay? This is how we started the second quarter. So we are now officially into the second quarter of the year, okay? So let's start with regression. So to get the data into your calculator, you're going to press stat, and then you're going to press enter to get to the edit mode. Okay, to find the regression functions, you're going to go stat, and then you're going to go over to the calc menu. Okay, to find the y values, think about what is a pirate's favorite key. Vars. So you're going to hit vars, going to go to y vars, and you're going to press enter. Okay, so vars, y vars, enter, right? And that'll give you the y's. Okay, all right. So I'm going to do a couple of examples. I'm only going to do the first two because the idea is basically the same for all of them. Okay, so Amory recorded the distance and height of a basketball when shooting a free throw. We need to find a quadratic equation for the relationship of the horizontal and the height. So here's what we do. We're going to go to stat, edit. Okay, you to clear out anything that's here, you go up, you hit clear, and you hit enter. Ours is already clear, and now we're going to type it in. So 0, enter. 2, enter. 6, enter. 9, enter. 12, enter. 13, enter. 15, enter. Okay? Here, 4, enter. Go over, right? 8.4. 8.4, enter. 12.1, enter. Okay, and so on. 14.2, 13.2, 10.5, 9.8. You should always give it an extra look over, especially if you have decimals. So 0, 2, 6, 9, 12, 13, 15. Yep. 4, 8.4, 12.1, 14.2, 13.2, 10.5, 9.8. Perfect. Okay. You're not always going to get a nice perfect thing going on here, so you really want to make sure that, right, and you're not going to know what the right one is, right? It's not going to be obvious, so you really want to make sure that you really hook this up correctly, okay? At this point, we want to go second, y equals, and we want to make sure that our first stat plot is turned on so we can visualize this data. And then what we're going to do is we're going to hit zoom, and we're going to hit option 9 to zoom stat. Okay, and really quick, what I'm going to do once my thing is done, it's going to take me a second. Still thinking, what's going on? Oh, okay, good. I'm going to just hit y equals, and I'm going to delete this graph. This is from the previous set of problems, so it doesn't show up there. So here's our graph. It looks approximately quadratic, and now what we're going to do is we're going to find the quadratic regression equation. So we're going to hit stat, calc, and we're going to do option 5, which is quadratic regression. Okay, so we have our L1 and L2. We're going to store the regression equation. We're going to go vars, y vars, function, y1. So when it's done, it's going to store the function in y1. Okay, we're going to calculate. We're going to take a minute to write down our equation. So what we have is 3 decimal places. So negative 0.118 x squared plus 2.112 x plus 4.215. That's the function. Okay? You could even write f of x is equal to. Okay? There's the function. Let's see what it looks like. So we'll graph it, and now it's been stored already in the regression function. Beautiful. Okay, also notice, and I don't know if you noticed this, what I'm going to do is I'm just going to rerun this regression. You notice that there's no r squared value. So remember, to show the r squared, you're going to go to mode, and you're going to make sure that stat diagnostics is turned on. Okay, and then if we do that, when I go back and I run the regression, you're going to see r squared is 0.96 if we round to the nearest hundredth. So that's a pretty good regression. Okay, now I'm going to come back to my graph because they want to know what's the approximate maximum height of the ball. So we just did this kind of what function are we going to use for maximum? We're going to use the max function. So second calc, maximum is option 4. My left bound of my max Make sure we got a healthy right bound. And hit the approximate middle, and let's see what it gets for us. Okay, so the maximum is, the max is 8.95, 12.63, but we want the height, so the max height is approximately, that's the y, 13.675 feet. Okay, because we want to use the y. All right, on to the next one. Now, notice how I'm clearly dictating the function that I want you to use. So I've clearly said, use cubic regression to answer. Okay. So the data in the table give the average speed of the Trident motor yacht for several engine speeds x. Okay, so the speed of the yacht based on the speed of the engine. Okay. Now, you see the word average. Don't get too wrapped up in that, because you're not actually doing any averages. The average itself is cooked into the letter. So when you see 6.43 here, for example, that is an average. You're not doing any additional math there. Okay, so I need a polynomial model, and in this case, I'm specifically looking for a cubic model. And in general, I would expect you to be able to do that. I would probably give you the model, so we're going to clear that out. Again, up to the top, not times, clear, because you'll get an error if you just have a symbol there. Beautiful. So let's type it out. 9, 11, 13, 15, 17, 19, and then for whatever reason, they couldn't just make it 21, had to be 21.5. So 9 goes with 6.43. 11 goes with 7.61. 13 goes with 8.82. 15 goes with 9.86. 17 goes with 10.88. 19 goes with 12.36. 21.5 goes with 15.24. Okay. Okay, and so basically what we're going to do now, we're just going to double check it. 82, 986, 1088, 1236. Perfect. We're now going to do our cubic regression. So we're going to go stat, calc. Oh, don't overshoot it. Cubic reg. Let's go ahead and store the regression equation. Vars, y vars, function, y1. Execute. Make sure you execute before you graph. All right, we're going to also round to the nearest hundredth. The r squared, look at that, beautiful. That's practically a 0.1. That indicates cubic regression is really, really a good choice. Okay, f of x equals, okay, so let's do 3 decimal places. 0, 0, 5, x cubed minus 0.194 x squared plus 3.132x minus 9.53, because 529, so it'd be 530. Okay, there we go. There's our function. All right, now let's see what it looks like. Oh, one thing I forgot to do. I'm going to let it graph through. Don't forget, you know why this isn't working? Because we need to do a zoom 9 to zoom stat. There we go. So now it's going to actually model it. Notice the curve going up. That's a pretty good sign. Again, context would matter here. And I'm going to estimate the average speed for 2400 RPMs. All right. So 2400, x is in hundreds. So 2400 indicates that x equals 24. So that I'm going to do on my calculator. Okay, or second, calc value, let x equal 24. See if we can figure this out. Ah, darn it. All right, so that's not going to work. Let's see if I can turn off the stat plot. Now graph it. So there's a couple ways we could do this. I'm going to try to graph it again. Now I'm going to do not trace. I could do trace, but I'm going to do second calc value. Let x equals 24 and see if we get an error again. Okay, that's all right. So here's what the other thing you can do. Here's a little hack. If you do second window to set up your table, you set your independent to ask. Okay? Then we go into the table, let x equal 24. Here we go. Y equals 19.406. In other words, this average speed of the trident is 19.406 knots. Okay? You could alternatively plug that in, and that would work as well. So here's how you plug it in. Second, let's quit that out. So you would do here 0.005 times 24. So it might be a little bit different of an answer, and that's because there's less. I'm doing more rounding here. So let's see what that looks like. 194. Sorry, this should be. I got to go back here real quick. I make that a cube. All right, so 0.194. And then we'd be squaring this thing. Come on. Good. Plus 3.132 times 24 minus 9.530. Let's see what we get here. So we're going to get about 23. I'm going to guess that comes from our rounding. Again, if I just pull a cubic regression real quick. So we did a lot of rounding here. And when you do rounding like this, you're throwing away a lot of data that is still relevant. So if you plug it in, that's completely fine. That's fine with me. But if not, please do some work to show I'm not going to write the work out, but I would say you on your test, because you're going to have more room, write out the work. So maybe I'll do this real quick. So write out. Show me what you're plugging in. Okay? Plus 3.132 9.530. Okay, and the reason there's a disparity is because I rounded up here. This was not supposed to be rounded up. And when you're rounding up, that has so much value, right, that's going to really skew everything that's going on there. Oop, not ready to go to compositions yet. So it's really going to skew everything that's going on there, okay? But in the reality, we know that this is fine for me. So you could say, if that's how you did it, you'd say 23.014 knots, okay? Lastly, what engine speed produces a boat speed of 14 knots? So here we'd probably go in and we would calculate this, because now I want to know if y is 14, what is x? Let's do a little trace. See if we can even get 14 on our graph. 13. Okay, so that's about 14. So we would say, for C, we could say about using our graph, 20.59 knots. Okay, so this is I give you x, what is y? This is I give you y, what is x? Okay, now the last one, again, I'm not going to do that due to time, but basically what I would suggest you do is the same idea. So the year since 1900 is your x, is your L1, immigrant population is your L2, year since 1990 is right, that's your L1, L2 rather. You do a cubic regression, so you plug these in for L1, and then don't forget the 60 through 100. You'd plug the corresponding these into L2. You'd get a cubic population. And then if I want the immigrant population in 2020, well, x equals what for 2020, right? Well, 2020 is how many years since 1900? It's 120 years. So then when you're done, you plug 120 into your equation, and then you would be done. Right? So please go back and make sure you understood what I did in this video. Then in a moment, I am going to move on to the next set of problems. All right, so now we're finally out of the regression and we're now into composition of functions. So remember, the regression unit this year was quick. It was just composed of more or less a little quiz, a little bit of introduction, but heavily a project determined the final grade in terms of that particular unit rather than a pen and paper test. So stuff you really want to know there. Composition of functions. So this was our next unit, and a composition, this is our unit on composition, inverse, radicals, okay? So 4 ways to write a composition using f and g. So remember, this is f of g of x. I've plugged a number into g, something's popped out, and it's plugged right into f. So one way to write it is f-o-g, fog of x. The other way to write it would be g of f of x. Now, these are not the same in most cases, but they're just two different ways, right? Because it could be either one, right? We could write f of g of x, okay? Or you could write g of f of x, okay? So these two go together and these two go together, okay? Just notation that you need to be aware of, okay? So here, f of x is on the left, g of x is on the right. So here we go. We need to find f of g of 1. So first, here's g. I'm going to label this. Okay, so g of 1, we come to g of 1, that's 5. We come in and plug 5 into f. That would be negative 2. So you're plugging into here, getting your y. You're taking your y, you're plugging it into f. G of f of 5. So f of 5 is negative 2. G of negative 2 is 3. Okay, so you're working inside out. G of negative 1. Okay, G of negative 1 is 4. 4 goes into f, negative 3. Oh, nope, thank you, Siri, but I do not care. Sorry about that. So G of negative 1 is 4. 4. F of 4 is negative 3. G of negative 3 is 2, okay? So remember, so this is basically the same as G of f of 4, which is the same thing as G of negative 3, and G of negative 3 is 2. Okay, f of 8. So I do f of 8, which is 1. I take that 1, I plug it back in, and I get 1. G of negative 2. So negative 2 goes in, 3 comes out. Okay, 3 goes in, 4 comes out, 4 goes in, 3 comes out. Okay, so it's interpreting using a graph. Okay, down here, we have functions. So we have f of 0. So first we plug in 0. So we have f of, so we plug in 0, we get 3. So f of 0 is 3. Now we plug in 3. 3 squared is 9. 9 plus 3 is 12. So we plug in 12. We get 144. Plus 3 is 147. So f of 0 is 147. Now we're going to do g of f of g of negative 1. So first, let's work our way out. So I have g of f of g of f, and g of negative 1. Negative 1 plus 2 is 1. Absolute value of 1 is 1. 1 minus 1 is 0. 1. Match this. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Now, f of 0. So g of f of g. Now, f of 0 is 3. 1, 2, 3. Now we're plugging in. So see how I'm working my way out. So now, g of 3. 3 plus 2 is 5. Absolute value of 5, 5. 5 minus 1, 4. So what I want to know is g of f of 4. Now I plug in 4. Okay. 4 squared is 16. 16 plus 3 is 19. So I actually want g of 19. 19 plus 2 is 21. Absolute value of 21 is 21. 21 minus 1 is 20. Okay? So that means g of f of g of f of g of negative 1 is equal to negative 20. So things we want to look for here are patterns to make this easier for ourselves. I did have a previous video where I did use patterns to be able to figure out which is which, and sometimes it will be helpful. So if you have the ability to do that, I definitely would recommend doing that. But that's the idea. You're just plugging in, getting an answer, and plugging it into the next function, and you start inside and work your way out. All right, so this is a quick little crash course on compositions. Again, I really encourage you to go back and check anything that might not be well understood, and then in a moment I will move on to the next concept. All right, now here we are at inverses, and hopefully Siri will not try to involve herself anymore. That would be ideal. So here we go. Inverse functions. The graph of an inverse function, okay, has to pass the horizontal line test, okay? It must pass the horizontal line test, okay? Now remember, the vertical line test, is it a function? Horizontal line test is what we call a 1-to-1 function. So a function is such that every input has an output. A 1-to-1 function means that not only does one input have one output, right? Each input has an output, but also every output is only associated with one input. That is 1-to-1, okay? So remember, in general, the graph of an inverse function is a reflection about y equals x. In other words, to graph it, you just remember flip the x and the y. So if 3, 2 is on the graph of f, 2, 3 is on the graph of the inverse. Okay, so in other words, if xy is on the graph of f, yx is on the graph of the inverse. All right, here's how I find an inverse. Really important, really important. I'll tell you, we get to college, we see pre-calculus skills that people still struggle with, right? So this is important. So first, replace f of x with y. Swap the letters, swap the x and the y's. Wherever you see an x, you write a y. Where you ever see a y, you write an x. Get y alone again, and then you replace y with the inverse notation. Okay, and in general, when you compose a function and its inverse, you get x, because if you apply the function and then undo it, you should be back where you started. For example, 5 plus 6 is 11. 11 minus 6 is 5. So by using the inverse of plussing 6 and minusing 6, if I apply the plus 6 and then the minus 6, I'm back to the original 5, okay? And that needs to happen both ways. So this is why we taught compositions first, because compositions are powerful in that they can confirm whether something really is an inverse. Okay? So now here I go. I'm now going to determine which relation has an inverse. And here we go. So I'm just going to do a quick little horizontal line check. This obviously fails. No, it's not even a function. So it's not even function. Here, it is a function, fails the horizontal line test. So not invertible. Here, passes horizontal, passes vertical. So yes, has an inverse. Okay, so we need to be able to look at a graph and see if that's the case. Okay, lastly, we need to find the inverse of each function. I'm going to actually add in another example because I feel like this is not enough for this one. So let's take a look. All right, so if I'm looking here, what I'm seeing is, let's go ahead and first step, we're going to write y equals 3/2 x plus 10. We'll swap it, x equals 3/2 y plus 10. Subtract 10 on both sides. Okay. Now, and this is tough, we're going to multiply both sides by 2/3. So I've got 2/3 x minus 10 equals y. And you could probably just leave it like this. F inverse of x equals 2/3 x minus 10. Okay? Now, let's test it out. Okay? So f of f inverse of x is, well, I plug f inverse into f. So I have 3/2 times 2/3 x minus 10 plus 10. So immediately these cancel. I've got x minus 10 plus 10. So that's x. What if it's the other way around? F inverse of f of x equals 2/3 3/2 x. So we have to look back here, right? 3/2 x plus 10 minus 10. So these are going to pop off. These are going to go away. And we get 2/3 times 3/2 x. These cancel. We get x. So this is truly the inverse we're looking for. Maybe I'll just do a circle so I don't have to worry about cutting through. There's my inverse. Okay. Here, f of x equals this one. Let's go ahead. So y equals 2, 3x plus 4 minus 7. Alrighty. And let's start by doing a flippity flop. So I got x equals 2, 3y plus 4 minus 7. So I'm going to start by adding the 7. X plus 7 equals 2, 4. Let's go ahead and divide by 2. X plus 7 over 2 equals 3y plus 4. Okay. And now we're going to go ahead and square both sides. Sorry. So I've got x plus 7 over 2 squared equals 3y minus 4. Sorry, plus 4. Now I'm going to subtract 4. So x plus 7 over 2 squared minus 4 equals 3y. So y equals x plus 7 over 2 squared minus 4 over 3. Very complicated, right? So that's our f of x, our f inverse of x, I suppose I should say. So x plus 7 over 2 squared minus 4 over 3. So let's see if we can figure out what would happen there. So if I was to plug root 3 plus 4 minus 7 in, so immediately what would happen was these would cancel. The 2's would cancel. The 7's would also cancel. So the 7's actually would cancel first. The 7's would go away because the minus 7 and the plus 7. Then the 2's would cancel. So I'd be left with square root of 3x plus 4 squared. So let me show you at least one way. So I'm going to plug in f of x. So I'm going to do 2, 3x plus 4 minus 7 over 2 squared minus 4 all over 3. So if I do this out, and then don't forget I've got a plus 7 in here too. Okay? From this plus 7. So these are going to cancel out. Then these are going to cancel out. So what I have essentially is 3x plus 4 squared minus 4 over 3. So then the root cancels out. 3x plus 4 minus 4 over 3. The 4's cancel. I get x. Okay? There we go. Now, there is a catch. It's not going to be perfect. This is technically only defined. We do have to clarify that x is greater than or equal to negative 4/3 because this has to be more than or equal to 0. Okay? So it's not like you can plug whatever you want in, right? because you can't plug whatever you want into there. Okay, I'm going to show you one last quick one. So let's let f of x equal 3x squared minus 5. Okay, now we know 3x squared minus 5. Well, the issue here is that it's not 1-to-1. So what we have to do is we have to specify such that x is more than or equal to 0. Because if we let x only be greater than 0, it will then have an inverse. Okay, again, I'll show you why. 3x squared minus 5. We graph this, right? See, it's not 1-to-1. So we're only going to focus on where x is more than 0. Okay, now we can do an inverse. So now, let's set y equals 3x squared minus 5. X equals 3y squared minus 5. So we add the 5. We divide by 3. And then we square root. So we have y equals the square root of x plus 5 over 3. And so therefore, f inverse of x equals x plus 5 over 3 square roots. Beautiful. Okay, and if we were to plug that in, 3x squared minus 5, the 5's would cancel, the 3's would cancel, we'd get just x because we'd have the square root of x squared. Okay, so this is how we do inverses. I hope you found this to be helpful. I encourage you again to go back and make sure you understood these problems. And then in a minute, we will move on to the next set of problems. All right, moving on to rational exponents. All right, so thanks for sticking with me so far. This is the next part of the unit that we did. So we did rational exponents and then we did radicals, okay? And these are actually connected to each other, right? So given the expression, x to the ab, b, the denominator, represents the index of a radical, okay? And so to recap, if I have the cube root of 7 index, this is what we call the radicand, the thing that we're taking the radical of, okay? And a represents a power. Okay, so here's some useful properties. So here's actually what it looks like. This is the same thing as the bth root of x to the a. All right, here's some useful properties. Just to recall from last year, x to the a times x to the b is x to the, you add the exponents. Here you fly high multiply. Here, what we would be doing is we'd be subtracting the exponents because of the canceling. X to the negative a is actually 1 over x to the a. All right. X over y to the a. Here it would be x to the a over y to the a, and a to the x, b to the c just means it's a to the x, a to the c. You apply the radical to the c, or the exponent to the c rather, and then you apply it to the b. So you fly high multiply. Some things we want to be aware of. Okay. All right, this is definitely a challenging unit for sure, and definitely a little bit of contention as well in this unit. All right, so 81 to the 3/4. So we have a index of a radical that's 4 and a power that is 3. So we can either cube 81 and then take the 4th power, or take the 4th power of 81 and then cube it. But I know that the 4th root of 81 is 3. The 4th root of 81 is 3. And remember, with even roots, you only do the positive root. Only the positive root. That is how it is defined. The 4th root of 81 is not plus or minus 3. It's 3. Okay? So now, we're going to take 3. We're going to cube it. We get 27. Therefore, 81 to the 3/4 is 27. 16 to the negative 1/4 is 1 over 16. We put it down to the bottom to the quarter. That means the 4th root of 16, which is 2. And we can actually confirm this. 16 to the power of negative 1/4. We should get 0.5. Yep. And we can actually see if we can 2-frac this. 1/2. Perfect. Okay. 125 over 27 to the 2/3. We want to do first flip it. Then we make the power a positive. So we need to do 27 to the 2/3. So the cube root of 27 is 3. 3 squared is 9. Right? Then the cube root of 125 is 5. 5 squared is 25. So therefore we get 9 over 25. All right? Here we need to apply the 3/2 power to the 16 and the x to the 22nd. So first we do 16, so it's basically 16 to the 3/2 times x to the 22nd to the 3/2. So here, 16 to the 3/2, so the square root of 16 is 4. 4 cubed is 64. 22 to the 3/2, you fly high multiply. So 22 times 3/2 is equal to 33. All right, here, you got to be careful. First, we flip the exponent. We flip the thing we're taking the power of. So it is 81 x to the 20 on the bottom, y to the 12 on the bottom. And we could do a 1 to the 1/4, but 1 to anything is always going to be 1, right? The 4th root of 1 is 1. 1 squared is 1. So we don't have to worry about that. To make sure, I didn't want anyone to think that was a negative. Where are we at? 1. Okay, 81. The 4th root of 81 is 3. Okay, so we fly high multiply. So x to the 20 to the 1/4, you multiply, you get x to the 5th. And then you get y to the 3rd because we fly high multiply there as well. Okay? Okay, moving on down. Similar thing going on here. So what we're going to do is we're going to do one piece at a time. And then we'll multiply in the end. So here we are going to have a 1 over. And we will tackle that in a second. So first, 9 to the 3/2. So 9, the square root of 9 is 3. 3 cubed is 27. Okay, now we're going to do x to the 12 to the 3/2. So that's 3/2 of 12 is 18. Then we're going to do 20 to the 3/2, and that is 30. 20, and essentially you're multiplying there again. Here we need to flip it, so we need to put the 81 down, and then we're going to do 81 to the 2/3. Now, 81 to the 2/3. Ooh, 81 to the 2/3. Well, here's what I know about 81. Bad news. If I try to take the cube root, I'm pretty sure. Let's see if we can do this. Yeah, not a whole number. Darn. All right. So we'll have to roll with it. But we'll see if we can clean it up. Yes, we can. So 81 to the 2/3. Okay, so 81 is equal to the cube root of 81 squared. Now, the cube root of 81, well, two numbers go into 81 that have cubes, 27 and 3. Okay, so basically 81, the cube root of 81 is equal to 3 times the cube root of 3. Right, let's try this out. 3 times 3 to the 1/3. third. And now let's do 81 to the 1/3. See, they are the same. Now we need to square that. And then that would give us, if we squared it, 9 times the cube root of 9. So ready? Let's square our answer. And then watch. 9 times 9 to the 1/3. Okay, so we can confirm on a calculator that that's what we need to do. So that's the best we can do. We can do 9 times the cube root of 9. Okay. And I'm okay with leaving a cube root down there for now. It's not the best, but we'll deal with it. All right, 2/3 of 12, that's x to the 8th. 2/3 of the 15th, that's y to the 10th. Now let's clean it up. So we leave a 3 up top. These cancel for a 3. We leave a 10 up top, x to the 10th, because you subtract. We leave a y to the 20th, because you subtract. And on the bottom, we have the cube root of 9. Now, technically speaking, we should multiply the top and the bottom by a number such that we would clean up the bottom, right? So we could multiply the bottom. We could multiply the bottom technically by, I don't know, the cube root of 3, because watch, the cube root of 9, because of the powers of exponents, 9 to the 1/3, the laws of exponents, right, times 3 to the 1/3 should be 27 to the 1/3, which is 3. So technically, we could do this. 3 root 3, the cube root of 3. Not 3 root 3, the cube root of 3. Okay, and if we do that, what's left is 3. It's called rationalizing the denominator. And then we have 3 times the cube root of 3 times x to the 10, y to the 20. Okay, technically, we could do it like that. All right, over here, again, similar split up. It's going to be a 1 over. So 20, negative 1. So this is negative. Just be careful. This is actually negative. So 125 to the 1/3. That's 5. 18 to the 1/3. That's 6. R to the 30th to the 1/3. That's r to the 10th, because we're multiplying. And that is s to the 7th. Okay, over here, we have 5. Square root of that, k to the 10th, r to the 7th, s to the 8th. Okay, so we're going to end up with a negative, because the negative times a positive. The 5s will cancel. We're going to have 4 k's up top. We're going to have 1 s up top, and on the bottom we're going to have 3 r's. Okay, due to the cancellation. Okay. All right, last but not least, we need to clear up some of these down here. So let's I'm going to show you what we got. So the square root of x to the 5th times the square root of x to the 9th. Well, that's the square root of x to the 5th times x to the 9th, which is the square root of x to the 14th, which is x to the 7th, because it's x to the 7th to the 1/2. Down on the bottom, what we have is we have x to the 8/3. Okay, so what we have is x to the 7th, right? Because that's the laws of exponents, which is the same thing as x to the 21/3 minus 8/3, right? And we know that 21 minus 8 gives us a number which is 13. So we have either we could write x to the 13/3 or the cube root of x to the 13th. Okay? You have to use your laws of exponents here. Okay, over here, let's do it like this. So this has to be power of 7 radical is 3, power is 13, radical is 3, power is 21, radical is 4. So let's start by combining. Multiplying is to adding, x to the 20 thirds over x to the 21 fourths. Okay, now on the bottom we need to subtract. So that's the same thing as x to the 80 twelfths over x to the 63 twelfths. And now the subtraction is possible. So that's x to the 17 twelfths, okay? Or the 12th root of x to the 17. So basically, it looks complicated, but all you're doing is you're applying the laws of exponents into radicals. So we're essentially going backwards and going from roots back to powers by thinking about this is the numerator, denominator, numerator, denominator, numerator, denominator. Then we're using the laws of exponents, the fact that multiplying means adding, dividing means subtracting, a little bit of cleaning up, and I just did this, again, because to subtract 8 thirds and quarters, you have to turn them into twelfths, essentially. All right, so please make sure you understand what we did in this part of the video. I encourage you to go back and rewind, and then in a second, we will move on to the next part of the video. Alrighty, here we go. Simplifying radicals, we're just simplifying them. That's it. Okay? So, when simplifying radicals, you do need to split up numbers and variables. Okay? So, you're going to do one at a time. We're going to do the numbers and the variables separately. Okay? To remove a number from the nth root, okay, you need to look for a factor of that number whose nth root is a whole number. So, for example, to remove from a square root, you need to look for a number that has a perfect square. So, for example, if I'm simplifying the square root of 8, I would choose 4 and 2 because 4 is a perfect square. When you're splitting up a variable, okay, this is a number. This is a number. Okay, when you're splitting up a variable, you find the largest power you can that is divisible by n, okay? That's less than the original power. So for example, x, the square root of x to the 29th. I'm going to split that up as x to the 28th times x, or x to the first, because 28 is the biggest power of x that's less than 29, all right? And also is divisible by the index of the radical, which is 2. And remember, if you don't see 1, you assume it's 2. All right? So here we go. We're going to go ahead and hook this one up. Let's start this. So lots of variables here. I'm going to do one thing at a time. So I'm going to split this up. I see this is going to be 81 and 2. This is going to be, ready, m. I'll do this underneath. M. Oh, that one's going to work out perfectly, though, because that's divisible, 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 divisible. So we're actually good here. So 9 will come out. The m to the 6th. So remember, this is like to the power of a half. So m to the 12th comes out as m to the 6th. P to the 18th comes out as p to the 9th. R to the 20th comes out as r to the 10th. H to the 12th comes out of 24 rather comes out as h to the 12, and then you leave a square root of 2 in your final answer. I don't want to see the square root of 2 next to the 9. It's technically not wrong. Let's get all the stuff that comes out perfectly followed by the stuff that does not come out perfectly. So please try to keep that order if you can. Okay? All right, what about this one? Now remember, it is a perfect cube, so that will work. When you pull out the number, please, if there's a negative in a cube, please try to pull that out. Pull out the negative. All right. This is divisible perfectly. This is divisible perfectly. And 4 plus 2 is 6, so that's divisible perfectly. So I get negative 3, k to the 7, because you divide by 3. H to the 11, you divide by 3. S to the 14, 14, 28, 42. Yep. And then what do we leave? Leave the cube root of 3. Okay? Because negative 3 root 3 is the same thing. Negative 3 times 3 root 3 is the same thing as the cube root of 81. So rather, negative 3 times the cube root of 3 is the same as the cube root of negative 81. Just want to make sure I said that correctly. Okay? So here, you're only worrying about taking out the number itself, splitting up the number. Okay? Notice how I did this strategy of making the little tree, little factor tree. That's a good strategy that someone pointed out this year. I really loved that. Thank you for that, individual. Okay? All right, moving down. Now I'm going to have to get a little bit more creative with it. This actually might work out perfectly. This one's going to be a little bit more of a challenge. All right, so I got 40, and I can see that 40 is going to be negative 8 times 5. And let's start with that. So that's going to be, and then 21, that'll work out perfectly. That'll be divided by 3. That'll work out perfectly. That'll be divided by 3. That'll work out perfectly. That will be k to the 14th divided by 3. So this is negative 2 e to the 7th n to the 11th k to the 14th times the cube root of 5. All right. Here, this is going to be 16 and 4. Okay. Now here, this is going to be r to the 12th because that's the biggest multiple of 4 that goes into 13, right? Times r. This is going to be d to the 6th. That's evenly divisible. And that's going to be m to the 7th because that's 28. And then we leave an m squared. Okay? So here we go. The cube root, the fourth root of 16 is 2. Okay, the r to the, now, the 12. We're going to do the 12 over the 4, so we'll have, that will be 3. We're going to do d to the 6 comes out perfectly. Okay, so m to the 30th, right? So we really should write this as 28. So the 28 we divide by 4 will give us 7. Then we drop our fourth root, and what's left? Any r's left? Yep, the fourth, 1 r is left. D's are all gone. Technically, we should put our numbers first. So let's drop, all right, we got this checked. Let's drop our 4. Got that done. We got to put our r in there. Now that's done. That was done. That was done. And there we go. So 22 r cubed d6 m 7th. This should be m 7th. Okay, so remember though, when you take a power out, that's the same as dividing its exponent by 4, and that again has to do with the laws of exponents, being that when you, for example, take the expression to the power of 4, you're multiplying the exponents. All right, now to the double black diamond. We need to now figure this one out. So I can see this is not divisible. None of them are divisible by 4. So it's going to be a challenge, but that's okay. 243. So I'm looking at 243, and I'm seeing 81, because 81's fourth root is 3. Okay, b to the 17th, I've got b to the 16th and b, because 16 is divisible by 4. Here I've got g to the 20th and g to the 3rd. And here I've got g to the 40th and g squared. And notice those add up to 17, 23, 42. Okay, so here, the fourth root of 81, 3. The fourth root of b to the 16th, b to the 4th. The fourth root of g to the 20th, g to the 5th. The fourth root of g to the 40th, f. Oops. Okay. F to the 10th. Now I drop the fourth root. Okay, there's a number remaining, 3. Okay, the 16th was done. We do have a b remaining in there. The 20th was done. We have a 3 remaining in there. The 40th was done. We have a 2 remaining in there. That's it. Okay. Last one to the fifth root. Okay, so we've got 32 and 10 because 32 is 2 to the 5th. The 32, we have n to the 30 and n to the 2. The 51, we have t to the 50 and t to the 1. And the 44, we have s to the 40 and s to the 4. Okay? So we, again, pull it out. The fifth root of 32 is 2. The fifth root of n to the 30 is n to the 6th, because we're dividing there. The fifth root of t to the 50 is t to the 10. The fifth root of s to the 40 is s to the 8th. Now we drop the fifth root, because again, you're just dividing. Okay? Remaining inside is 10. Okay, n squared is remaining. T, you could write t to the 1th, I'll take it, but you don't have to. And again, if it was like a multiple choice, I would not expect to see the power of 1 displayed. I would just expect to see the letter s to the 4th. Okay, and we can check our work, by the way, by doing this. So 2 to the 5th is 32. 32 times 10 is 320. Good. And 6 times 5 is 30, because if we were to put it back in, we'd have to do it to the power of 5. So 6 times 5 is 30, plus 2 is 32. Good. 10 times 5 is 50, plus 1 is 51. Good. 8 times 5 is 40, plus 4 is 44. Good. Okay, so it all works out. Okay, so that's how we simplify radicals. I hope that this made sense to you. Again, please go back and make sure you understand what I just did here. And then in a second, I will move on to the next problem. All right, here we are. We're going to do a little bit of radical arithmetic. All right, so let's talk through this. To do radical arithmetic, here's what we need to remember. When you're adding radicals, the index and the radicand must be the same. Radicand. For example, if I have 2 times the cube root of 7 plus 3 times the cube root of 7, that's 5 times the cube root of 7. Okay? But that's because these are equal. So we almost think of them like letters. Okay? If I did the 4th root of 7 and the 3rd root of 7, those are not going to combine. Those are different things. Okay? When multiplying radicals, only the index needs to be equal. Okay? So to multiply you just multiply the radicands and then bring the product under one radical. Okay? When dividing radicals, okay, you must, okay, rationalize the denominator by multiplying both numerator and denominator by the conjugate. And remember, conjugate is similar. We talked about in this video complex conjugate. The conjugate of square root of a plus square root of b is just the square root of a minus the square root of b. It's the same idea but with square roots. And when you multiply them, what you just get is a, because it's like a squared minus b. That's it. All right. Notice though, sorry about that. Irrational, rational. Okay, so it's rationalized. All right, let's simplify here. All right, here we go. So to simplify, what I'm going to do is I'm going to take a look. So cannot combine these. They are not the same. But here's what I can do. 20 is 4 times 5. 45 is 9 times 5. So I can do this. This can become 3 times 2 root 5. This can become 5 times 3 root 5. Okay? And here, this would become a 6 root 5. You'd multiply the numbers. This would become a 15 root 5. You'd multiply those numbers. You bring them together. you get 21 root 5. All right, that's all you do. Here, I'm going to now do this. I'm going to do 16 and 108. I'm not a huge fan of this because I want to clean this up first. I don't like this. So what I'm going to do is I'm going to make this a -8 and a 2. And I bet you 108 is divisible by 7. Or by 27, rather. 27. It is. So this is 27 and 4. Okay. So what I have is minus, let's just draw a little thing in there, minus 2 root 2, 2 cube root of 2, times 3 times the cube root of 4. All right. So what that lets me do is we'll multiply the whole numbers, -6, and this will become the root of 8 because you multiply and bring in, and then this is the same thing as -6 times 2, which is -12. Okay. Now on the other hand, 108 times -16, -1728, which, to be honest with you, let's try to take the cube root of that. -12. Now, I don't think this the square root of the cube root rather of -1728 is obvious, so that's why we'd want to clean those up. Here, let's rationalize square root of 6, square root of 6. These are going to cancel and just become 6. Here, I'm going to get 3 root 6 plus the square root of 12, which I do need to simplify. So it would be 3 root 6 plus 12. Well, that's 4 and 3. So that's 2 root 3 over 6. And then these can simplify a little bit. No, they cannot. No, Mr. Moray, don't do that. They cannot. Because these are not all divisible by the same thing, right? 2 and 6 cancel, but their factor is 2. 3 does not have a factor of 2. So remember, you can only simplify if all 3 things have the common factor and if you divide by that common factor. So if this had been 4, for example, divide by 2, divide by 2, divide by 2, that would have been okay. But they do not have a common factor, so dividing is not possible there. Okay, moving on down. Let's take a look here. So we're going to, again, do some simplification. The first thing we notice is that the roots are not the same. So yikes, that's not going to pan out. We're going to have to clean up. Okay, so this I notice is 27 and 3. This is 8 and 4. This is 8 and 3. So I've got -2 times 3 cube root of 3 minus 3 times 2 cube root of 4, okay, plus 5 times 2 cube root of 3. So it's combined. So I've got -6 cube root of 3 minus 6 cube root of 4 plus 10 cube root of 3. Notice this cannot combine because different number under the radicand. These can. So it's 4 cube root 3 because this and this are like terms minus 6 cube root of 4. Beautiful. All right. All right. Now 64. Let's tackle this next one. This is tough, but this is 16 and 4. And let's see if I can crack this. So I believe 40,000. I believe, no, that 10,000 has a fourth root. Let's take a look. So I'm going to multiply it by 0.25, which is 1/4. It does. So this is 10, 3, 1, 4 by 4. So this is -4 times, 2, fourth root of 4 times 2 times 10 fourth root of 4. Okay, now the fact that the roots are both 4 does not really matter. They're equal, it doesn't really matter. So negative 8 fourth root of 4 times 20 fourth root of 4. Okay, now this becomes negative 160 fourth root of 16. And the fourth root of 16 we know is 2. So it's equal to negative 160 times 2, which is negative 320. Okay, and we could actually check that. Negative 4 times 64. And again, I'm going to use the 0.25 power. So, sorry, again. Negative 4 times 64 to the 0.25. Oh, no. Let's make sure it's 64. We're not going to get the right answer. All right. Negative. Let's try this one more time. Negative 4 times 64 to the 0.25 power. Here we go. Times 2 times 40,000, 3, 4, 5, to the 0.25 power, negative 320. Beautiful. All right. Last one on this row, we're going to multiply by the conjugate, 2 minus root 6, 2 minus root 6. So here's what's going to happen. Here you're going to have 2 times 2, that's 4. Matter of fact, might have to do some simplifying. Okay. Plus minus 2 root 6 plus 2 root 6. The root 6's cancel out. Minus the square root of 6 squared, which is 6. And so 4 minus 6 is just equal to negative 2. So that's what's on bottom. Okay, because again, it's 2 squared minus square root of 6 squared. Up top, we get 8 minus 4 root 6 minus 2 root 6. Okay, here, careful, plus 6, because it's negative root 6 times negative root 6. Negative times negative is a positive. Root 6 times root 6 is 6. Okay, so what we get is 14 minus 6 root 6 over negative 2, which is the same as negative 7 minus 3 root 6. Actually, plus 3 root 6. Okay? If we divide both by negative 2. All right, so that's what we're doing. We're just simplifying. We are just rationalizing the denominator here. Okay? Last one, what we're going to do here is we're just going to go ahead and do some squaring. And squaring just means, right, multiplying by itself. So 2 minus 2 root 10, 2 minus 2 root 10. Okay, so it's going to be 4 minus 4 root 10 minus another 4 root 10. Now, here's the challenge. It's going to be a plus because it's negative times a negative. Well, 2 root 10 and 2 root 10, that's 4 root 100, which is 40. Okay? Because think about it, the 4's and then the root 10 becomes a 10. Okay? So we add them up, 44 minus 8 root 10. Here, multiply by the conjugate, 7 plus 4 root 8, 7 plus 4 root 8. So on the bottom, I get 49, it's going to be a minus 16 times 8. Okay, on the top, I get negative 21 minus 12 root 40, because you combine those. Nope. Thinking ahead of myself. No. Minus 12 root 8. Okay. Now here I get plus 14 root 5. Now we have the plus 8 root 40. Okay, so here, let's do the bottom. 49 minus 16 times 8 equals, okay, negative 79. Up top, you know what I mean? Not much we can do here. We could do this as 4 and 10 at best. So we have, not really any combining at all that you can really do here. So you have negative 21 minus 12 root 8 plus 14 root 5. And then this becomes 2 root 10. Right? Because this is square root of, this is 4 and 10. So this becomes 2 root 10. The 2 multiplies with the 8, and you get 16 root 10. Okay. All right, so that's how we simplify these. Again, I hope you understood what went on in this part of the video. I did do some of the work, not directly here. So again, I'll just show you this is 8 times 2 root 10. That's where that comes from. Please make sure you understood every part of this video. Of course, again, write down any questions you might have. Rewind if necessary, and then in a moment we will move on to the next part of the video. Alrighty, here we go. Home stretch. Equations with radicals and rational exponents. All right. So now we're gonna go ahead and we're gonna solve equations. Okay. So and this came up actually with the systems that we just did. So we did have some kind of semi-review recently. Okay. So to get x by itself in this equation, what you need to do is you need to raise both sides to the power of b over a, and that is because when you do x to the a over b to the power and you multiply by x, or rather you do to the power of b over a, you get, they're going to fly high multiply, these are going to cancel, and you just get x to the 1. So that's the idea, right? You're getting x alone. When with working to the radicals, you should generally try to get the radical alone. That will make it easier. That will eliminate how much you're squaring. So you should try to get the radical, particularly the most complex one. Remember, the opposite of squaring something is taking the square root, and the opposite of taking the square root of something is squaring it. Okay? Whenever you get a solution to a radical equation, you always plug it back in. You always do that, because if it doesn't make both sides equal, it's called an extraneous solution. Remember, the reason we get extraneous solutions is because when we work with a radical, we need to square both sides. For example, here we're going to have to square both sides. When you square both sides, you often create a quadratic. Now, a quadratic has two solutions, right? But just because you created a quadratic, that doesn't mean that both of those solutions are going to work. So you always make sure every single solution you plug it in, because there's a high chance that you will get an extraneous solution. Okay? All right. So here we go. We're going to start here. We're going to square both sides. So we get 9r equals r squared. All right. So we have r squared minus 9r equals 0. So we factor. R times r minus 9 is 0. So we get this. Either r is 0 or r is 9. Let's check that, right? 9 times 9 is 81. Square root of 81 is 9. Perfect. R times 0 is 0. Square root of 0 is 0. Perfect. Now we plug it back in. That actually worked. So these are both going to work. Okay, over here, here's what we're going to do. We're going to take both sides. First, we're going to divide. We want to get the this thing alone. So I'm going to divide both sides by 5. Notice that 1080 is conveniently divisible by 5. I know that because the last digit is a 1 or a 0. So I've got 216 equals a to the 3/2. So you do this first. Now I raise both sides to the 2/3 because these cancel and give me 1. Okay? So now we need to do 216 to the 2/3, and I believe 216 to the 1/3 is going to work out. Yep. So this is equal to, so a is equal to 6 squared, which is equal to 36. Okay? And I will try to keep the perfect cubes on the board, so you'll have access to that. All right, let's check our work. So 36. So the square root of 36 is 6. 6 cubed is 216. 216 times 5 is 1080. Perfect. Alrighty. Not an easy one. Let's take a look at this. This one might not come out completely perfectly. Hopefully it was meant to be done like this, because what I'm looking at is some interesting stuff, for sure. Now, I want to get the root alone. It's not going to be as simple as, the radical is going to be an issue, right? So I'm going to start by squaring both sides. So squaring clears this. This, you can't just square one at a time. I'm seeing that mistake happening a lot, so we have to be careful. So we get 16. Okay, so here's what it would look like. Okay. So we get 16 plus 4 times that, minus, plus another 4, so that's plus 8. Now we get minus 8 minus n when we square the square root, okay? Just want to clean that up because we want to make sure we know that's a 3. I see that as a mistake waiting to happen. All right. Let's clean this up. So what I get is I get 8 minus n equals to the 16 and the 8 become an 8. All right. The minus n becomes a minus n. And I get 8 times. All right. Alrighty. So that's interesting. Off the bat, I'm noticing that things are going to cancel, it appears. Yeah. Okay. Because when we had the roots cancel, it looks like, yeah, right? Because -4 is a 16. So it looks like we're going to be left with 0 equals 8 minus 8 minus n, which means that 0 equals minus 8 minus n. So n equals -8. Okay, I know that because I divide, I get 0. I square both sides, I get that. And so n equals -8. If n equals -8, 8 minus 8, or minus -8 is 16. So on the left, I get 4. Remember, you always check your work. -8 minus -8 is 0. But, so this has no solution because this, you can never have a negative number come out. Okay? And -8 minus -8 is going to be 0. That's not going to work out. So this has no solution. That's very possible. Okay? Over here, let's solve this one. So I start by adding the 10. I divide by 3, and I believe, let's just be careful here, 729 divided by 3 is the same thing as dividing by -3. So I get 3a minus 60 to the 5/3 equals 243. Now I'm going to raise both sides. This to the 3/5. This to the 3/5. So basically 243, 3, 9, 27, 81, 243. This is 3. 243 to the 1/5 is 3. That's 27 when you recube it. I add 60. 3a equals 87. Yep, and then 8 plus 7 is 15, so that's evenly divisible. So 3 goes into 8 twice, remainder of 2. Wait a minute, that's not possible. 87 divided by 3. 29. Yeah, it goes into 23. I don't know why I thought 27. It's 29. All right, check our work. 29 times 3 is 87. We just saw that based on the calculation I just did. 87 minus 60, that would be 27. Okay, so now I'm at 27. The cube root of 27 is 3. All right. 3 to the 5 is 243. 243 times negative 3 is negative 729. Negative 729 minus 10 is negative 739. Okay, now I'm going to come down here, and what I'm going to do is I'm going to solve this. So what I'm going to do is I'm going to move the 4 over, because I don't want to do a square. Like, this was really, what was really annoying is that I had to FOIL and I had to do a square, but there was a root as part of the square. I hate that. And if I don't have to, I won't do that. So here's what I'll do. Okay, I'll keep the root, negative 3m plus 10. And then I'll slide the 4 over so I get this kind of situation. Now I will square both sides. So on the left, that goes away. Here I get m squared minus 8m plus 16. Okay? Now I'll combine, so I'll get 0 equals m squared. So I have to add 3m to both sides. I have to subtract 10. Nice. So I get m minus 3, m minus 2. So m equals 3 or m equals 2. Let's take a look. 3. So what I get is 3. So that gives me 3 times 3 is 9. Oh, let's see if that, I don't know if that's going to work. It doesn't work. I don't know. Well, the problem is, right, if 4, right, so let's go back and see if it works here. So first of all, 9 minus 15 is 6. Negative 6 plus 6 is 0. 4 minus 10 is negative 6 plus 6 is 0, right? Let's check it here. 9 plus 1 is 1. 9 minus 24. 9 minus 24. So that works. Okay. Negative 6 plus 10 is 4. 4 minus 16 is negative 4 is negative 12 plus 16 is 4. So 3 and 2 individually work. So the problem is that, again, you plug back in, they do not work. Okay? And I know this has got to be m squared minus 8m plus 16. We know everything is working, but when you plug back into the original, well, if you add a positive number to 4, you're never going to get to a lesser number. So neither of these work. So again, we're looking at no solution. Okay, so you have to be ready for that. I put a lot of the no solutions in here to get you to check those answers. Okay, now coming over here, we're going to start by doing both to the power of 5/4. So 5x minus 3 is going to go ahead and be equal to, so the 4th root of 16 is 2. The 5th root of 2 is 32. So 5x equals 35. So x is equal to 7. Let's check the work. 35 minus 3 is 32. 5th root of 32 is 4. 4 to the 4th is 16. So that works. Okay. So the idea is, again, 1, isolate the more complicated square root if you can. In this case, the reason I did not move that root over, the reason I did not do that is because it would have been really difficult to do a root and a root. If I had done that, I would have been like, it would have been really, really tough, because I would have had to do square root of 8 minus n and square root of negative 8 minus n. First of all, they can't combine because they're not being multiplied. That would be cool if they could. But what I'd have is I'd have square root of 8 minus n minus 2 square root of 8 minus n, square root of minus 8 minus n. And what the heck do I do with that? That would have been really hard. So you don't want to be squaring when you have two square roots on the same side. That's not going to work out nice for you. Do not do it. But in general, try to isolate the complicated square root if you can. All right, so hopefully this part of it made sense. Again, I encourage you to go back and take a look at anything that might have been confusing. And then in a moment, we will move on to the next part of the problem set. And here we go. This is the last part of the problem set that was created by me. We will have a little problem set that was I found online that was contextually based as part of this, but this was the last section that was created by me. And I do have an answer key to this that I posted for my class, but I will go through this as well so everyone understands. So this is just on circles, okay? So to begin, the standard form of the equation for a circle with center h, k, and radius r is as follows. X minus h squared plus y minus k squared equals r squared. This comes from the Pythagorean theorem, okay? So basically, if I look at a point on the circle, the distance away from the x squared plus the distance away from the y squared has to be equal to the radius squared, right? Because again, we think about the Pythagorean theorem, right? A squared plus b squared equals c squared. So it's just an extension of the Pythagorean theorem and essentially the distance formula. Okay, so if I'm going to do this circle, I'm going to have x plus 2 squared plus y minus 5 squared, that locks the center in, equals 3, because, nope, see, I made that mistake too. That's a common one, equals 81, because it's the radius squared. Okay, so that's a really common type of problem that I might put on a midterm, would be like, give me this equation, and like maybe one of the answers would have it be a 3, so we'd be square rooting it, do that extra unnecessary backward step. Maybe one would be a 9, right? Maybe one would be an 81. Maybe I'd flip the points around. Okay, so things to think about. All right, write the equation of a circle that meets each of the following descriptions. So it's got a center of 2, 6, and a radius of root 5. So I would do x minus 2 squared plus y plus 6 squared. That locks in the center. And then I need to do the square root of 5 squared. So that would be a 5. Pretty straightforward there. Here, these points are on the endpoint of the same diameter, meaning the center is the midpoint of these points, right? The center, if given any circle, right? If this is a diameter, the diameter always passes through the center, and therefore the center is the midpoint of any given diameter. Okay, so the midpoint of 8 and 2, so we'd have 5. Okay, and remember, to get the midpoint, you add the x's and divide by 2. So 8 plus 2 is 10. So it's literally the middle of the 8 and the 2. The number in the middle is the midpoint. Okay, now, what number is in the middle of 2 and negative 4? That would be negative 1. Okay, and again, in my head, I added them and divided by 2. And if you think about it, 2 plus 3 is 5. 5 plus 3 is 8. Negative 2 minus 3 is negative 1. Negative 1 minus 3 is negative 4. So it's right in the middle. So here's my center. Okay, so here's how I start. X minus 5 squared plus y plus 1 squared equals r squared. Now, if 8,2 is, or 2,4, for example, is a point on the circumference, that means that if I plug in x and y, both sides have to be equal. So here I go. 8 minus 5 squared plus 2 plus 1 squared. So in other words, this equation needs to be true if these are going to be endpoints on the same diameter. So I do the subtraction. This becomes a 3. This becomes a 3. This becomes an 18 because it's 9 plus 9. So my final equation is this. X minus 5 squared plus y plus 1 squared equals 18. And what's cool about this is, if I wanted to find the distance, right, I could do the distance formula, right? Look, 5, the difference here, so this would be 3. This would be 3. I could use the distance formula if I wanted to, But I actually think it's kind of cool and shows some ingenuity. If you actually just plug in one of the points, you solve for r squared right away, and you plug that back in, okay? All right. Now I'm going to put each of these equations to standard form, and I'll include, let's state the center and radius. Okay, so again, what we want to do is we're going to complete the square. This is a really important SAT question. This actually separates 800s and not 800s. I'll tell you, I had this come up, not easy. I had to interview for an SAT tutor. I had to interview as an SAT tutor, and I had to solve an equation like this. It was gnarly. So, here I go. So notice as I was talking, right? I'm not good at multitasking. I separated the x's and the y's. I moved the -4 over. Now I'm going to complete the square. So I'm going to divide 14 by 2. That's 7. I'm going to square it for a 49. I'm going to divide -12 by 2. That's -6. I'm going to square it for a 36. Here, I'm going to add, don't forget to add 49 and add 36, because what you do to one side, you need to do to the other side, okay? So on the left, let's factor x plus 7 squared, okay? Let's factor on the left. On the right part, y minus 6 squared. And notice that this is b over 2, okay? And then I've got to do -4 plus 49 plus 36 equals 81, okay? So we have a center of -7, 6 and a radius of 9, because 9 squared is 81. Here, I'm going to need to do a little bit of arrangement. So I've got x squared plus 8x. I'm going to take the y squared and I'm going to move it back over. And I will leave the 64 because I want to have the whole number there anyway. Here, what I'm going to do is I'm going to add 16 because that's 8 divided by 2 squared. Here I'm going to add 1. So I'm adding a total of 17. And as you're going to see, I'm so creative with my radii. I'm so creative. So this is x plus 4 squared. This is y minus 1 squared. And that is 81. So again, similarly, I'm going to have a center of -4, 1. And again, I'm going to have a radius of 9. Okay. Okay, lastly, what I'm going to do is I'm going to do this one. And so what I'm going to do is, again, I'm going to collect my terms. So I'm going to do x, not ready to complete yet. So I've got to do two things here. First, I've got to convert. I've got to perform the transformation, and then I need to write the final version once I've transformed. Okay, so basically what I have is x squared plus 14x plus y squared plus 12y equals, now 100 minus 24, that would be, or rather 24 minus 100, that would be -76. So now I complete the square, 49 plus 36, okay? Okay, so over here I've got x plus 7 squared, y plus 6 squared, and now over here I'm going to do -76 plus 49 plus 36, giving me +9. So that's my original. Now I need to translate 5 to the right and 7 up. So when you do this, this is called a rigid transformation. So a rigid transformation is one such that everything is proportionally preserved, meaning the points remain the same distance away from each other and the center, such that the shape of the circle stays exactly the same, the radius stays exactly the same, but the points are all going to move the same amount. So I start at -7, 6. My new center, C prime, so I take this and I move it, I'm at -7, I go 5 to the right, that puts me at -2. I'm at 6, -6, I go 7 up, that puts me at 1. So my new formula is x plus 2 squared plus y minus 1 squared equals 9 because the radius stays the same. Okay? And that is all I have to do there. All right, so hopefully this page made sense to you. Again, if not, I encourage you to go back and take a look and make sure you understood everything here. And then in a moment, we will move on to the final section. All right, folks, here we are. We are on the final part of this video. And so just due to time, on this piece, what I'm going to ask you to do is take a look at this little link. What we have is a wonderful person has gone ahead and already put together a really awesome answer key on this. So I'm going to ask you to just follow this link right here to the answer key, because this will really have all of the problems that we have here broken down. If you have questions about this, of course, feel free to ask me anytime. But I just feel like the answers are already there. I'm happy to walk through it with you. But again, the answers are there. This is just applying rules of polynomials. And I'm going to kind of leave it at that. Again, I'm happy to break it down. I'm not saying it's not important, but I feel that because it's already been created by someone else and the answer key is out there, and I'm not expecting you to be able to do this. I mean, I'm not expecting you and saying, you can't seek the answer key out. I'm going to ask you to look at that. So again, we want to go to this link right here. As of when I created this video, this should be active, and check it out. All right. So, and overall, I hope you found this video to be helpful to you. Again, think about all the questions that you've had so far. Make sure you review the video in full. If you can, it's greatly appreciated. If you have not done so, I recommend you seek me out for your notes. So I'd be happy to give those back. And just keep at it. It's not easy stuff, but it's stuff that if you're committed to, you can do it. All right. So keep at it. Don't forget to love math. And remember, you can do it. All right. So keep working at it. Keep asking questions, and have a wonderful day.